but also take advantage of other coupling. And this is what I want to show you today. So conventionally in spintronics, we have used ferromagnetic, non-magnetic interfaces. We flow a charge current through the interfaces, and we will generate what we call the spin accumulation zone, which is the out of equilibrium situation, which allows you to go from a spin polarized to non-spin polarized current at equilibrium in ferromagnetic and non-magnetic interface. So this generates the spin currents, and these spin currents and this spin accumulation zone are responsible for the giant magnetoresistance, tunnel magnetoresistance effect, spin transfer torque, and so on. This can be achieved by flowing a charge current, but also by using a heat gradient, dynamical spin injection, like using spin pumping. Using spin orbit coupling, now we will go back in a situation where we flow the current along the interfaces and along a material. This is, for example, the case when we use a spinel effect in a non-magnetic material, where we will have out of a charge current the generation of a transverse spin current with the development of spin accumulation at the boundary of the slab. By using also the Edelstein effect, the Rashba at interfaces, we can also generate a spin to charge conversion. And this is one of the key aspects of spintronic. And using spin orbit coupling, we can go from metal spintronic to semiconductor, oxide, magnetic, and topological insulators. So some words about the spinel effect. The spinel effect developed in the materials bulk, and we do a spin to charge or charge to spin conversion. There are three basic mechanisms responsible for the spinel effect: the skew scattering or the side jump scattering. There are intrinsic effect and also intrinsic contribution arising from the bond structure. Basically, the spin, the transverse resistivity will be expressed as a combination of a linear and two quadratic term linked to the longitudinal resistivity. And for the spinel angle, you will divide by the longitudinal resistivity, and you will end up with this expression. And you see that to, for example, increase the spinel effect, you can play with the longitudinal resistivity to some extent. So this spinel angle is the ratio between the spin and charge current. And in direct and inverse cases, this is the same parameter, the same spinel angle, that link the conversion efficiency. So this has led to a very large amount of literature in field. And there are some debate in the spinel angle of the material, even for a material as simple in a sense as platinum. Or as studied as platinum, people are not yet agree on the spinel angle. One thing I would like to emphasize is not that only the spinel angle that is a key parameter, but also the resistivity and associated to that, the spin diffusion length. In Rashba or interfaces or 2D electron gas, more generally, we can use what is called the Edelstein effect to convert charge to spin. So these are some cuts in energy in the K-space. And here you have a Fermi contour for a topological insulator. So you have a Dirac cone, and you just cut at some energy of this Dirac cone. And what you see is that you have a circular Fermi contour with the spin momentum locking. So a charge moving in K-space along this direction as is spin that is locked transverse to this displacement. And this is reverse when you reverse the K. So if you inject a charge current, it's like moving the Fermi contour, and you see now that you will have out of equilibrium situation where you will have an excess of spin down, of spin up here, and out of a charge current, you will generate a spin accumulation. So in the case of Rajba interfaces, sorry, I forgot to mention. So here you have two Fermi contours with opposite chirality. Respect to topological insulator, this spin accumulation is blurred by the inner counterclockwise contour. So in principle, topological insulator should lead to larger spin accumulations. The reverse effect is also possible if you inject out of equilibrium spin accumulation in those 2D states. You will induce a shift of the Fermi contour because you inject excess of spin up, let's say. So you will shift the Fermi contour and then generate a charge current. This effect has been predicted by Edelstein in the 90s. In the following of the talk, we will mainly use spin-to-charge conversions because we have a quite easy technique that is called spin pumping to generate spins that we will inject in the material that we are studying. So we do that by putting the sample in the EPR cavity. We make some contact on the side of the slab. We apply a DC field plus a small RF field that at the resonance condition, ferromagnetic resonance condition, will ensure the precession of the ferromagnetic material, here CFB, cobalt iron boron, in this case. By doing so, you will inject a spin current into an attached material. This attached material appears as a sink. It will take out of angular momentum from the ferromagnetic material, ensure an extra relaxation. And this will occur through the transfer of angular momentum and through a spin current. And this spin current will eventually be converted into a transverse charge current. So this is an example of the raw data. This is the derivative of the absorption FMR spectra. And at the resonance condition, we have, for example, in the CFB platinum sample, the development of a Lorentzian shape signal at the resonance. So we use FMR, we generate a spin current, then we will use the conversion mechanism, spinol or Rajba, that will generate a voltage in open conditions. To quantify this injected spin current, we need to study the extra relaxation that is due to the presence of the strong spin-orbit coupling. And so this is by doing broadband FMR. We vary the frequency. We study the increase of the line width of the resonance spectra. And we see that, for example, in CFB alone, here we'll have, or it's probably permalloy, I think, we have 8 to the 8 10 minus 3 of Gilbert damping. Whereas when we attach to permalloy platinum, we increase to 12 10 minus 3 the Gilbert damping. So this extra Gilbert damping is directly related to this loss of angular momentum, this extra relaxation channel that we have opened by attaching metal, for example, here to the ferromagnetic material. So one important thing, of course, the analysis of the signal, we should respect some symmetry. For example, if we rotate in the cavity the sample by 180 degrees, we should reverse the signal. And out of this, generated voltage, we will get the charge current production, that is simply the voltage that develops, taking account the internal resistance of the sample. When we have started by studying the Rajba, we have first focused on silver bismuth case, which is well known for having through RPS measurement a very large spin orbit coupling. So we have deposit nickel ion on top of a silver bismuth stack, and what we have identified that if we have silver, neither silver or bismuth alone give a large signal, and it's only when we form the bismuth silver interface that we have a large signal. So it was important to have this interface, and this is how we identify that the Rajba origin of the conversion in this case. And the other thing we figure out is that here in this experiment, we inject a 3D spin current and we get interfacial charge current. So the ratio between those two currents has necessarily the dimension of a length, and we call it inverse Edelstein length. In the case of silver bismuth, this length is around 0.3 nanometer. And this length is related to two important parameters, the Rajba coupling, indeed, but also the Rajba strength, but also the relaxation time. So if we can play with on both parameters, we might be able to increase the inverse Edelstein length. So this is the outline of my talk. So as I said, by going beyond the case of 3D and 5D methods, using a semiconductor, oxide, topological insulator, we can get new properties involved, but also new coupling. And this is what I want to emphasize today in my talk, is that in topological insulator, there is not only one, but two surfaces that will play a role in the interconversion, the top and bottom surfaces of a slab. That in Rajba system, in oxide, we can take benefit of the complex bond structure and tune the Fermi level through a gate to have quite interesting features in the conversion, and some module will be able to tune the conversion. And also, finally, if we are able to take advantage of the ferroelectricity, we might be able to have a bipolar and remanent control of the spin charge conversion and tune this conversion by applying a gate voltage that is much more energy efficient than applying a current. So the topological insulator I will present today is mercury telluride. So why mercury telluride? Mercury telluride is a material that is well mastered in Grenoble, in Leti, with Philippe Ballet. And he has an inverted bond structure. And if you induce a strain, like by growing it on the cadmium telluride, you open the gap. They have identified by ARPES that there is Dirac cones. Here is a TEM image, STM image of the sample. So we have mercury telluride and cadmium mercury telluride barrier, and we see through the annular signal that the chemical interface extends only around the two atomic planes, around 1 nanometer. So the growth is well mastered, and in the group of Tristan Meunier and Nel Institute, they study the quantum transport in this system, and they observe a very nice quantum Hall effect with very nice plateau in the transverse conductivity and really vanishing longitudinal conductivities. And so one interesting thing also to mention in this material is that we have a very large mobility, close to 500,000 at low temperature. Just to show you the first interest of this material, I just compare here the spin pumping experiment with a nickel ion layer deposited on the mercury telluride and compare with a platinum. The platinum is the blue curve. So there are two interesting features. The first interesting feature is that the mercury telluride induces a much smaller broadening of the line width of the resonance spectra, meaning that we have much less loss of angular momentum, much less relaxation when we attach mercury telluride to nickel ion respect to platinum. Second interesting feature is that the produced current is 3 times larger at room temperature respect to platinum. So we have, in one hand, we inject less spin current, but we generate much larger charge current. So the Edelstein length that we then estimate in this system is up to 2 nanometers. So in silver bismuth, it was around 0.3 nanometer. And also what we confirm through the sign is that we have a helical, the helicity of the Fermi contour, and that is here counterclockwise. One important thing when we put metals on topological insulators, and especially this compound has very volatile species, is to be sure that you don't have intermixing at the interface. And for that, we find out that it's important to insert a barrier between the two materials. And so here it's a mercury cadmium telluride layer. And if we study the produced charge current as a function of the thickness of this barrier, we see that there is an optimum at some finite thickness of this mercury cadmium telluride insulating barrier. This leads to a larger charge current production respect to a sample that is in direct contact. And if the barrier is increased, of course, the charge current production decrease. If we now study for a fixed barrier the different thickness of the mercury telluride, so this is the Edelstein length as a function of the mercury telluride length, and you see that we have a very distinct thickness evolution respect to what we have in the case of platinum. In the case of platinum, you have sinus hyperbolic rise of the signal, and here we rather see a kind of optimum, a peak at some finite thickness. So how to understand this ferrature? So first an increase and then a decrease of the conversion efficiency. So if we have mercury telluride that is thin enough, we might have a coupling between the top and bottom surfaces. This has been shown in bismuth sennelide. If you have not enough quintuple layers, you will have a coupling between the top and bottom surfaces, and you lose the polarization because the two surfaces have opposite chiralities, and you need to have a thickness that is large enough to uncouple these two surfaces. So this is the case in mercury telluride, and in mercury telluride, bond structure calculations show that you need to reach something like 25 nanometers to avoid the overlapping of the two wave functions from the top and the bottom surface. The other thing is the effect of the bulk conduction. The sample is not perfect. There are some defects, and also then a contribution from bulk states. It's not only the surface states, but also the bulk. And this can be seen when we study the temperature dependence of the mercury telluride as a function of its thickness. For thick layers, we only see a rise of the square resistance as a function of the temperature, revealing the freezing of the bulk state. And when the sample is thin enough, we start to see the predominance of the metallic surface states. So in that case, this has been shown in the group of Saito, that if you have too much bulk state, you have a reduction of the conversion efficiency of the inverse Edelstein length, because the bulk state had a relaxation channel that will decrease the effect of the spin to charge conversion in that case. So to sum up, we have first an increase of the signal that is due to the decoupling of the top and bottom surfaces, leading to an increase of the effective polarization. And then we have at two thick layers the rise of the importance of the bulk state that leads to a decrease of the signal. So we inverse Edelstein length, effective inverse Edelstein length through this expression. And in the case of mercury telluride, this optimum is around 30 nanometers. So now I'll switch to oxide, and especially on the STO, strontium titanate, where we have Rajba and two-dimensional electron gas at the interface with STO with several materials deposited and a complex bond structure that will allow to modulate the conversion through gate voltage by rising or lowering the Fermi level. So this is a work that we are doing in collaboration with CNRS Thales, Manuel Bibes and S. Barthelemy. And so we have started with STO LAO, which is known to give rise to a two-dimensional electron gas at the interface between STO and LAO. So we have deposited a nickel ion layer on top and do the dynamical spin injection through spin pumping. And here are the raw data that we obtain. So we have a nice Lorentzian curves that are well reversed by reversing the field direction. And this signal is very large. And for example, respect to nickel ion on top of LAO, substrate of LAO, and there are almost no signal in that case. While when we have the STO LAO system, so with the two-dimensional electron gas, we have large development of a transverse voltage. So in that case, the inverse Edelstein length is around 6 nanometers here at low temperature at 7K. So it's quite a giant respect to silver bismuth. And the other very interesting feature is that we can modulate in amplitude and sign the conversion as a function of the gate voltage. And we attributed these features to the fact that we go through this complex bond structure with several bonds involved with different chiralities, with explaining why the signal can be either positive or negative. Rodel et al. Have shown that, in fact, on STO, you can form quite universally some two-dimensional electron gas. For example, by depositing aluminum reactive metal on STO, you will reduce the STO. The aluminum will get some oxygen, create some oxygen vacancies that will act as donor for developing the gas at the interface. So this has been shown by Arpace. STO by itself, it's insulating, but if you deposit aluminum, you start to observe metallic states at the surface. King et al. Has also found that at some peculiar point of the bond structure, you have some anti-crossing, and where you can have some bond inversion. So this has been called a non-trivial topological points. And we expect that the spin-orbit coupling can be enhanced by the hybridization of the bond at the vicinity of the anti-crossing points. So not only aluminum can create a two-dimensional electron gas at the surface of STO, but several metals, as soon as they can react with oxygen and take out some oxygen from the STO, you can generate quite universally two-dimensional electron gas. So this is evidenced by this experiment, XPS experiment, where you see that when you deposit aluminum on top of STO, the aluminum will oxidize. Whereas on the other hand, the titanium is reduced, going from 4 plus for the bare STO sample to situation where you have titanium 3 plus and 2 plus. So you can infer from the takeout angle the extension of this titanium 3 plus reduction, and you found that is around a few nanometer, and this is confirmed also by STEM EDX and ILS experiments, where you see the titanium terminated interface with the aluminum on top, and you does see that the aluminum is getting oxidized. You have extension of oxygen in the aluminum layer, and you also see the change of the oxidation level of titanium as a function of the titanium plane number respect to the interface. And so aluminum reduces STO. If now we measure the sheet resistance of the sample as a function of the temperature, we can extract from a two-channel model the contribution of the two-dimensional electron gas in the aluminum nickel ion respect to the solar case of nickel. So there is an extra conducting channel in the case of the aluminum nickel ion sample respect to the bare case of nickel ion. Through electrostatic backgating, we can also extract through the whole measurement the carrier density, and we found quite a large carrier density in the case of aluminum STO sample, starting from when we deplete from around 710 to the 13 carrier density per square centimeter, and at large positive gate voltage that it goes around 10 to the 14. So we have much larger doping in this case respect than LAO. So we can higher in the bond structure. So this is the raw data of the spin pumping at several gates, minus 140, minus 10, and plus 100 volt. And you see that there is a nice symmetrical signal. Is almost no antisymmetric contribution that is well reversed by the field, but that is also reversed by the gate voltage. So we also here have a modulation of the amplitude and the sign of the conversion. So this is the full gate dependence of the inverse Edelstein length. So it looks a bit messy with several crossing change sign along the gate voltage, but with some peak value that are quite large, around 30 nanometer or above 25 nanometer at least, so much larger than in the case of STO LAO. So with our collaborators in Geneva and Halle, there was the extraction from ARPES of the bond structure of this STO aluminum sample at similar carrier densities. We see that we have 4 bonds involved in the energy cut, and where we had also the spin degeneracy. So we have 4 pairs of bond involved, and in Halle, they calculate for this bond structure the Edelstein tensor. And we'll see how this can be linked also to these peculiar points in the bond structure, like this anti-crossing. So if now they calculate the Edelstein tensor, and we will see along energy, while rising the energy, how we are in the bond structure. And so at first, there is only the first 2 pairs of bond where there is almost no signal. When the second pairs of bond arrives, we start to have an increase of the signal up to the case where the third pairs of bond arrive at the Fermi level. This bond is with opposite chirality. So we start to have a decrease and even a negative sign when it becomes dominant. Then we have some extremas where we have some crossing between bonds and hybridization in between the bonds. So we can completely map the expected conversion as a function of the position of the Fermi level within the bond structure of STO. And one very interesting point is that at this anti-crossing point is not that we have a maximum of the conversion. The maximum of the conversion is due also to a complex chirality of the bonds, and especially one Fermi contour, one chirality has a large polarization, while the other counterclockwise chirality has a vanishing of the polarization. So this large signal at this peculiar point is due to the fact that one of the bonds has a reduced polarization, so it blurs less the chirality offered by the first bond. So this is the experimental data, and I think that you agree that it's quite similar with the calculated Edelstein tensor. So the last point I would like to show you is that if we are able with this STO,
you are already running out of time. If you would like to show something about the last section, just go in a couple of minutes, please.
So here we can have a bipolar and remanent control of the spin to charge conversion. If we have a ferroelectric material below a SOX system and we reverse the polarization of the ferroelectric material, we might be able to reverse the chirality of the Fermi contour. And this might be extremely interesting in the case of the magnetoelectric spin orbit devices by Intel, to control the sign of the readout current of the element, and the memory element will be stored in the ferroelectric state and not in the magnetic state of the smaller energy consumption for writing information. This evidence the fact that we have induced at large electric field, induce a ferroelectric-like state in STO. We can see the polarization as a function of the temperature, which vanishes around 60 K, and that leads to a change of the square resistance of the sample. And if we do the spin to charge conversion, we see that we have either a large positive or large negative current production that is remanent and bipolar here. And by applying pulses of positive or negative voltages, we can change the sign of the conversion. At remanence, the inverse Edelstein length is extremely large, around 60 nanometer. And we check also that this remanence stays stable over several hours. So with this, I would like to thank Paul Noël, who has done all this spin pumping experiment, Diogo Vaz for the growing the STO sample, and Johansson and Goebel in Halle for the bond. Here are my summary.
Yes, thank you for the very nice talk. So if you have questions, please use the raise button option, or if you would like also, I could read the questions by using the chat. So while people will start making questions, so I would like to ask about the first part on the cadmium telluride. So you showed that you have an increase of the spin to charge conversion up to 30 nanometers.
Yes.
Isn't it quite large, this thickness would expect maybe the maximum to be somewhat a bit lower.
Yeah, the mercury telluride, that it's quite a clean system. In the calculated wave function extension is quite large, in fact. So you see that they overlap at 15 nanometer, while at 25 nanometer, they start to not overlap anymore. So, the quality of the sample makes that the wave function can extend quite far away. And this is indeed something that is probably not found in bismuth selenide, where this wave function extension might be of only a few nanometers.
Okay. So we have a question from Emmanuel Martinez. He asks for in the two-dimensional electron gas in LAO-STO interface, I can see that the first two DXI bands are filled before any EZ-DX.
Yes, yes, exactly. This is here. This is point one. Yeah. So here we have almost no conversion. Starting from the second band that we have. Indeed, the YZ-ZX band, the green one.
Okay. Yeah, if there are no more questions, I would like to thank the speaker and move to the next invited talk, which will be given by Professor Martin Grathan, who will talk about optimizing the spin Hall effect for material design.
Hello, good morning, everyone. Thanks to the organizers for having me and for organizing this. You can imagine it's quite an exercise to organize a complete online conference. Just to clarify, I'm not professor, but never mind. Thanks also to Laurent to introducing the spin Hall effect already quite nicely. And he highlighted right at the beginning that there is, even on a simple material like platinum, the controversy of how large the spin Hall effect actually is. And if you take home anything from that talk, the main theme is going to be there is no such thing as the spin Hall effect of platinum. You need to look very carefully, what is the configuration, what is the system, what are the interfaces, what are the surfaces, what are the perturbations. And in all these different cases, you might find completely different spin Hall angles, even for a simple material as platinum. So that's essentially the message of the talk, but I try to highlight that with a few more specifics. Before I start, let me introduce some of the people who contributed.
Don't forget to share your screen.
Sorry. Yes, I will do that. I was so excited about starting. Can you see it now?
Yes, please.
Very good. So let me talk about the people who have contributed to that work. So the experimentalists who have contributed are the group of Yoshihiko Itani in Tokyo, Laurent Villard, CNRS, Yasuniemi in Osaka University, and of course the group of Felix Casanova in San Sebastian. The theoreticians who have contributed here are the group of Ingrid Mertig in Halle, the group of Christian Heiliger in Gießen in Germany as well, the group of Hubert Ebert in Munich, and then I have also a collaboration with Western Digital, where Derek Stewart is working with me on these systems. Before I really start, let's do some geography and history. I'm from Bristol, so Bristol's in the United Kingdom. And you can see here a map of Europe, but also of the European Union. Obviously, Britain has decided to leave the European Union, which I would say, unfortunately. We only find out next year what that actually means for us. So if you don't know where Bristol is, it's here on one line with Cambridge, Oxford, and Bristol's here at the Bristol Channel. It's where Robinson Crusoe started his journey, so it's an old harbour town. Okay, so what is the spin Hall effect? Sometimes people suggest that this is all very fancy and quantum mechanical, but basically this exists entirely classically. This would be the Magnus effect there. And one example of this is if you nicely hit a football, you can nicely curve it around, hit the goal, even if normally that would not be possible. So that's essentially the classical analogon of the spin Hall effect, and I will come back to that in a second to even highlight the various different contributions to this. Good. So the basic spintronic application, the most simple spintronics application of the spin Hall effect you see here. So you have a non-magnetic material, you pass its charge current through, and in complete analogy to the classic example, you will generate a perpendicular spin current, which is then able to enter this ferromagnet, and using spin transfer torque or spin orbit torque, you might be able to switch the magnetization of that ferromagnet, and you essentially have a data storage device with that. Immediately, you see a couple of key features here. So when we talk about, spin currents or spin accumulations are generated in this non-magnetic material, then of course, initially we start talking about this bulk material, let it be platinum, gold, copper, whatever. But of course, it should be immediately clear that here at the interfaces, you might see a lot of different effects, and it's not entirely obvious how much of the spin currents you generate are actually coming from the bulk or are entirely interface related. And this is something I'm going to address in this talk. Of course, in addition, any such device preparation will not generally create perfect interfaces. So what you're going to have is impurities of the ferromagnet and the non-magnet, impurities of the non-magnet and the ferromagnet, and all this will contribute to different mechanisms and to different results in terms of your spin Hall effect. So what are the macroscopic mechanisms contributing to the spin Hall effect? I will mainly focus on two, the intrinsic and the extrinsic. And for the extrinsic, I will mainly focus on the skew scattering mechanism. So what is the intrinsic? The intrinsic is, as I said, classically it would be the Magnus force. So we have here a flow of air around an object, and as soon as you start spinning that object, the air will be moved upwards, and because of that, you will of course have a resulting force on that object pushing it down. And this movement of a spinning particle in air is the entire analog of the intrinsic spin Hall effect. Of course, in order to describe it, it's slightly more involved. So if you would have here a simple band structure, one band energy as a function of momentum in a periodic crystal, you can easily write down the velocity of such a particle, and the velocity would just be the dispersion, first derivative of energy with respect to k. But as soon as you have more than one band, this electron will feel the vicinity of all the other bands, so you actually have to correct this trivial velocity with what is called anomalous velocity. And this anomalous velocity is already linear in the applied electric field. So this is why it's called intrinsic, because you don't need any scattering. Already the velocity from the perfect crystal is linear in the electric field. The proportionality constant is here, what is called the Berry curvature. I will come to that expression in a second. What is important, it's perpendicular to the electric field by the cross product, so it will always be a perpendicular effect to the electric field. So what is the Berry curvature? The Berry curvature can recast in this long expression. Here are our periodic part of the Bloch wave function. You have derivatives of the Hamiltonian. But what I would like to highlight here is that in the denominator, you have a difference between energies. So this is immediately telling you that every time you have near degeneracy, so bends are coming close, this term in the denominator is getting small, so the Berry curvature is getting large. So this correction only and always arises if you are near degeneracies in your bend structure. So what do we need? We need large intrinsic spin-orbit coupling. This is hidden actually in this derivative of the Hamiltonian and this cross product, because this expression in the numerator tells you your Hamiltonian needs to be complex, and this is what spin-orbit coupling provides. It goes from a real Hamiltonian to a complex Hamiltonian, and that gives rise to the Berry curvature. And you need multi-sheeted Fermi surfaces. You need all those near degeneracies to get a big effect. Then what is the extrinsic effect? And being in Britain, of course, I have to talk about cricket here. So imagine you have a spinning object, you throw it, and this object hits a perturbation. And now we can see it very nicely. The object is spinning, it's our electron, it hits a perturbation, and then it moves to one side. And this is the extrinsic spin-Hall effect. In order to describe it microscopically, we have to invoke the Mott or skew scattering. So I have again to raise Sir Neville Mott because he was in Bristol for a while. So what is this about? So you have an impurity region here, you have an electron coming in. Let's assume the spin of this electron points into the plane and it moves this path. Then you can calculate the angular momentum of that particle. And in that scenario here, the angular momentum would point into the plane. If you then consider the energy contribution arising from spin-orbit coupling, you can take the scalar product of the spin with the angular momentum, and this contribution would be a positive contribution. So this would increase the energy of this configuration. In contrast, if you take the other spin, the spin points out of plane, then this energy contribution becomes negative, telling you that this is the preferred configuration. Electron with the spin pointing out of plane will move that way, while an electron with the spin pointing into the plane will move the other way. And this is causing the extrinsic spin-Hall effect. Now, how do we calculate that? Just very briefly, we consider the real space impurity problem in our semi-classical description of the spin-Hall effect. And we start with a periodic crystal. It's infinite in all three directions at this instance initially. Then we cut out a region still embedded in this perfect crystal, and we replace one atom there with an impurity atom. And what we do then, we self-consistently solve this impurity problem, calculate the scattering from an incoming electron to an outcoming electron, calculate this scattering probability here. This not only gives us access to the skew scattering, it also gives us access to the spin relaxation time in principle, which I'm not going to address during this talk. But as Laurent highlighted already, this is another crucial parameter for any spintronic device. Then if we have this scattering probability and relaxation time, what we solve is the Linear-Boltzmann equation, which you can find here. If you would ignore this vertex correction term here, you would not get access to the skew scattering contribution. In relaxation time approximation, there is no skew scattering. And if we solve this integral equation here, which we solve iteratively, we can calculate the conductivity tensor and the spin conductivity tensor to find the spin-Hall effect. So just to put that together, this is the spin conductivity or charge conductivity tensor. This is the extrinsic contribution, which is highlighted here. And this part is the intrinsic contribution. And all those things we can calculate from a fully relativistic density functional theory method, which in our case is the Karinga-Cohen-Rostocker-Green's function method. So here's an example of the anisotropic Fermi velocity on the Fermi surface, the anisotropic relaxation time, the effective mass on this Fermi velocity, and this is how the Parry curvature of copper, for example, would look like. So it's important to take all this anisotropy into account to actually describe real materials. So let's see how it looks like for real materials. So this is an example of a 3D crystal. We put a dilute concentration of various impurities in this 3D crystal. In that case, the crystal is gold. And you can see that for the spin-Hall angle, the ratio of the spin-Hall conductivity divided by the longitudinal conductivity, you can get any size, any sign. You can, for light elements, you can get up to 10%. For heavy elements, you can get only just about 2%. And in between, you have even a sign change. Now, if you do the same calculation for a crystal like copper, put the same impurities in, you get high effects for heavy elements and smaller effects for light elements as impurities. But again, you can find any contribution. So this only addresses the skew scattering, the extrinsic contribution. Now, of course, you might ask, when do we actually see those contributions? And to understand that, here I show you a result by our collaborators in Munich, the Hubert-Ebert group. These are calculations done by Stefan Lowitzer. So what they did here is they, instead of using the semi-classical approach I presented you before, they do a full Kuber formula description of the spin-Hall effect. So this includes all the various mechanisms. And if you follow this full square line here, so what this is a binary alloy, gold, platinum. On the left side, it's pure platinum. On the right side, it's pure gold. And this triangle would be the intrinsic value here. And you can see how in the dilute limit, where the concentration of platinum on this side gets small and the concentration of gold, the concentration of gold gets small here and the concentration of platinum gets small here, it diverges from this straight line. And this divergence is precisely where the skew scattering kicks in. And we can immediately see another important result here, that while on the platinum-rich side, the deviation is small, the deviation on the gold-rich side is quite dramatic. And this is basically the reason why people tend to use platinum, or one of the reasons why people use platinum is because they tend to get more similar values in experiments because impurities have not that big of an effect as on the other side they would have. Now, Laurent already introduced the scaling in principle, so this is now plotting the same data slightly differently. So this is the spin-Hall connectivity versus the longitudinal connectivity, and you can nicely see this linear behavior as you are in the skew scattering region and the extrinsically dominated region, and in between we have this not easily predictable curve connecting those two straight lines. In addition, what I said before, it's quite evident that on this side, on the platinum-rich side, the numbers are basically the same as the intrinsic platinum, whereas on this side, the gold-rich side, we have a dramatic change of the spin-Hall connectivity depending on the concentration. All right, so to summarize this transition between intrinsic and extrinsic, so if you want to use the extrinsic skew scattering mechanism, it's nice because it's easily tunable. It will be dominant in the clean limit only. So as soon as you're in the dirty limit, as soon as you have a high resistivity, you won't see this extrinsic contribution. The other advantage or disadvantage, depending on what you want to achieve, is constant. The whole angle is constant with the longitudinal resistivity. On the other side, the intrinsic contribution, it's often very robust for a large parameter range because it's dominant in the dirty limit. And the whole angle still scales with longitudinal resistivity. So making the resistivity larger allows you to increase the hole angle. To show you an example, this is done by the group of Felix Casanova here. So this is data, the spin hole angle of platinum as a function of the conductivity of platinum. And you nicely see how it initially follows here this linear slope. And then this is in the dirty region where you have a high resistivity, low conductivity, but then it ends away from it as you reach the extrinsic superclean limit. And as you can see here, for a simple material like platinum, you can tune the spin hole angle between 1 and 10%, depending on how clean you create your system. Another example of that, and now very commonly used as well, is tungsten. And what you see here is the spin hole conductivity for alpha tungsten, which is the BCC phase. So at the Fermi energy, which is here, the numbers are somewhere around 1,000 centimeters inverse. But the alpha tungsten is not what is used in experiment to have a large spin hole effect. What is used in experiment is actually the beta tungsten, which is a 15 structure. But what you can see is actually that the spin hole conductivity is not that dramatically higher. That's maybe just about a factor of 2. So that's not that exciting actually. But it only becomes exciting when you look at what are the longitudinal resistivities of beta tungsten and alpha tungsten in comparison. So there is a factor of 10 in between. And if you then calculate the spin hole angle, then that should be beta here. The spin hole angle for the alpha system is just 3%, whereas the spin hole angle for the beta system reaches 50% in such an estimation. So the point with beta tungsten is that it is only a metastable phase. So typically people grow it with the addition of oxygen and nitrogen to stabilize this phase. So what we did is we explored what effect does this oxygen have on the system. So what you can see here is those were the intrinsic values. This is the intrinsic value for alpha tungsten. This is the intrinsic value for beta tungsten. And then if we dope alpha tungsten with a little bit of oxygen or nitrogen, you get opposite sign contribution. So in the worst case scenario, these completely cancel and you get a very small contribution. Then we calculated still intrinsic contributions, but with a large admixture of oxygen, and you can see this actually reduces the spin hole conductivity for beta tungsten, while at the same time the pure extrinsic skew scattering contributions you can completely ignore. They are not even visible on that scale. So there is no extrinsic contribution in beta tungsten really at these impurity concentrations. So if we put that all together, you can see here all the dots and crosses and triangles. There are various experiments. You see here on the y-axis the spin hole conductivity as a function of thickness for beta tungsten and alpha tungsten. So you can get a large variety of conductivities. And for the highest ones, which are presumably beta tungsten stabilized with oxygen, this compares reasonably well to our calculations. If you would assume beta tungsten is homogeneous dope with oxygen, then actually we would predict a rather low spin hole conductivity. So our prediction or our assumption is that the oxygen actually moves to the grain boundaries of the beta tungsten. But of course, that's we can't describe grain boundaries really within our calculations. Okay, with that I move on to actually consider the thin films and interfaces I have highlighted at the beginning, because so far those were all perfect bulk calculation, including impurities, but still I considered only 3-dimensional bulk systems. So let's look first at the absolute extreme case. One monolayer of a noble metal. I consider here copper, silver, and gold, with two distinct surfaces, the 111 surface and the 001 surface, for in-plane impurities and atoms. And you can see, if we look at the spin Hall angle, then for this case of gold at the 111 surface with bismuth impurities in plane, you can reach 80% of charge to spin conversion. So this is almost perfect conversion. The reason for that is, one can show that in detail, but the principal reason for that is there is no interband scattering because you have only one band in one monolayer noble metal. And the confinement to the plane means there is no out-of-plane scattering, so everything stays in plane, which makes the effect so large. Now, the question was, is there anything special about gold? Why is gold that big in comparison to copper and silver? And to understand that, here you can see this is the same data you have seen before, but now as a function of energy. So let's assume we could change the Fermi energy of the system so slightly. So let's only focus on the red curves here. Those are the spin Hall angle. And you can see that for gold, it's rather an accident that we are actually hitting this peak of the spin Hall conductivity or the spin Hall angle. For copper, there's similarly high values, but we just happen to be with the Fermi energy slightly away from there. So that means we could reach the similar effects for copper and silver if we are able to reach those regions here. And so what we did as an example is this brown line is the copper system you saw. The yellow line is the local density of state for the bismuth impurity in gold. And what we did then is we took a copper system but put it in the lattice constant of gold, so applied strain to the system, which moved this impurity level to the Fermi energy. And if we do that, we can actually move the low value for the bismuth impurities in copper to the same high value as for gold. So with a little bit of strain on the copper system, you can actually reach the same values as for the gold system. So what happens at interfaces? Let's consider that configuration. So this is now a periodic configuration of cobalt, copper, and we periodically repeat that system in the X direction and also in the Y direction. So we consider what happens if the charge current is applied in Y direction. So this would be this direction. And what is the resulting spin current through that interface between copper and cobalt. And this is the full result. Let's focus only on the spin Hall angle here. So this line here is the spin Hall angle bismuth impurity in a pure cobalt crystal would generate. This is the number which a pure copper system with bismuth impurity would create. And then you see what would be the spin Hall angle as we place the bismuth impurity at those different places. And first thing is you dramatically reduce the bulk effect. That's one feature. The other thing is that you can dramatically change the spin Hall angle depending on where the impurity sits. So if we assume the impurities move to the boundary between the two systems, then we get a much larger effect than if we would only be able to place those impurities at the center of the copper layer. But that is still the situation where you have, in order to calculate conductivities, we had to invoke periodicity in this X direction, which is of course artificial. In a real scenario, we don't have this periodicity perpendicular to the interface. So what is the last thing we considered is actually the pure spin accumulation at its surface. So in that instance, we are not able to actually calculate a conductivity in this direction, in the X direction, because there's a vacuum, then we have a thin film of copper and vacuum on the other side. So the conductivity is by construction 0 in that direction. So the only thing we can look at is spin accumulation at the interfaces or at the surface. So again, we apply a charge current in the Y direction and we explore what is the spin accumulation at those interfaces. And we looked at two approaches, the Boltzmann approach, which is basically based on the method I've shown you before, and then also a full Kelder-Shannon equilibrium approach. And you can see that the agreement between the two approaches is, first of all, very nice. Secondly, you can see that all the spin accumulation happens right at this interface layer. Nothing else is really showing up. All the spin accumulation happens at those interfaces, or surfaces in this case. So you can imagine that as soon as you perturb those ever so slightly, any quantitative value is really possible. So the prediction of what you would get in a real device is not trivial from those calculations. With that, let me briefly highlight one more system. Namely, we have been talking about spin-orbit coupling. All this is generated by spin-orbit coupling. So obviously, we can say, oh, let's try to make spin-orbit coupling as big as possible. The biggest in a pure crystal we can get is uranium, because that's the heaviest metal we have and can deal with, to some extent at least. Theoretically much easier than experimentally. So what you can see here is now the intrinsic spin-hole conductivity for 3 phases of uranium. The gamma phase is the metastable BCC phase, and you can see for that phase the spin-hole conductivity is incredibly small. It gets a little bit larger for the stable alpha phase, and only for the HCP phase, the hexagonal phase, it gets reasonably big. There exists actually an experiment, and the experiment found an incredibly low spin-hole conductivity for uranium. So our prediction would be that this is mainly a BCC thin film they explored there, rather than what they assumed, the alpha crystal. With that, very briefly, in 1 minute, let's highlight what our next steps are, or at least what we are trying to do next. We would like to combine those spintronic approaches with superconductivity. So what is the idea here? In conventional S-wave superconductivity, you combine always a spin up with a spin down electron. So if you combine those, there is no magnetism and nothing exciting for spintronics could happen. However, if you combine this with conventional superconductivity, there you can get what is orbital magnetic moment. So the contributions of conventional spintronics can become relevant because this becomes now a magnetic object. And what are the basic ideas? So the advantage of superconducting spintronics would be low power, it could be potentially fast, and of course you can have new physics. The problem is of low temperatures. If we are talking about conventional things, you are at 10 Kelvin. The idea would be that you have with superconducting Josephson junctions, you have proximity effects, and if you add spin-orbit coupling, you can generate spin-hole effects in superconductors, so create magnetism in conventional superconductors as well. So we have been working on that, and we have now a working code, a working density functional theory code, where we can calculate the band structure of, or the quasi-particle band structure of conventional S-wave superconductors, in that case, niobium. It has to be noted we treat the interaction as a parameter in such a calculation, so that would be the normal band structure of niobium. If you use the Bogoliubov-Zhejan equation, you get a mirror image of all the bands at the Fermi energy, which is here. And if you then switch on superconductivity, there opens a gap around the Fermi energy, which is slightly more highlighted here. And then just to showcase what we can do, this is now a surface of lead where we place changing lengths of a chain of manganese atoms on it. And you can nicely see how this manganese atom creates in-gap states. So this is the density of states out here. This is the gapped region. And as we move through different lengths of the chain, we can move this in-gap state through the gap. And this is precisely where conventional superconductivity, magnetism, and spintronics is going to meet. And with that, I'm at the end of my talk. To summarize what I've been showing you, the spin Hall angle can be tuned, switching between intrinsic and extrinsic contribution. What I highlighted already at the beginning, not every platinum is the same platinum. You have to be very careful what you're talking about. The intrinsic spin Hall angle is typically more robust and can be tuned by sample resistance. Beta tungsten, I haven't spoken about beta tantalum, show the highest spin Hall angle in simple metals. Interfaces and surfaces can dramatically change what we observe. So again, one should be careful what one is talking about the bulk property of a material or about a surface or interface to another. And this is just an outlook what we want to do next to combine all this with superconductors. Thank you, everyone.
Yeah, thank you, Martin, for the nice talk and overview on the spin orbit coupling effects in materials. So there is a first question. So, well, be reminded that you can either use the raise hand option as well as write questions in the chat. So the first question is from Felix Casanova. So he wonders why in the copper layer there is no long spin realization of the spin accumulation at the edges, but it stays very confined.
I'm not sure I understood the question. You're talking about that?
The thin copper layer.
Yes. Can you hear me, Martin?
Yes, I can hear you.
Yes. I'm talking about this, that everything is very confined at the edges.
Yes.
I would expect because it's copper, it would relax because the spin diffusion length of copper is generally very long.
I agree. Partially, we don't know for sure. These are very fresh calculations. As you can see, they are not published yet. So partially, this is obviously, it's a very thin film we are looking at. So we are talking about 9 layers of copper here. So there's not much which can possibly decay and happen. In addition, you need things to be symmetric or anti-symmetric around that point. So just for symmetry reasons in this configuration. So I would imagine things will extend ever so slightly if we make this film actually thicker. But this gets dramatically more expensive in terms of calculations. So we practically can't make it much thicker. We have observed that if we take other materials, it becomes even more localized to the surface. So it really all happens to the surface, at the surface.
Thank you.
So I have a question. So how would you explain to experimentalists? So how is possible that the case for when you have, for instance, platinum with high resistivity, so the intrinsic effect dominates, but when it's clean, so it's the extrinsic that that plays a major role. So how you would explain this in a few words to grasp the qualitative explanation of the effect?
I think the easiest is the picture. So you can see you have the intrinsic number for platinum is this one, and the intrinsic number for gold is this one, right? In the large region in between, you basically connect with the linear line between the 2 points. Which then means if they are not dramatically different, those 2 points, then for most of the region, you get a very similar number as platinum would have.
All right.
If, for example, the other side intrinsic value would be negative, then in a 50-50 alloy or in a 28 alloy, you might actually find a negative or zero contribution coming from the intrinsic spin Hall connectivity. Yeah. So what you have to realize is that while we say in the dirty regime you see the intrinsic, it's of course the numbers is not the same as here, right? This number is slowly going smaller, but it's very close. So to experimental accuracy, you would say that's basically the same number.
Mm-hmm. So you would mean that that in case that you change the material, so the the impurities that you have in the system, then you could have a different picture. So for
Exactly.
instance, of platinum, for instance, you have only defects or structural defects, or you have certain kind of impurities, you would maybe change dramatically the effect of intrinsic and extrinsic and
yeah, but that's precisely the point. What you see here for platinum, the effect of extrinsic only kicks in very, very late. So you need to get to really, really pure platinum to see the extrinsic effects. Yeah, and that's why for platinum, we experimentalists tend to get very similar values. You have to do a lot of effort to see the different contributions. Whereas here on the gold side, people have presented in an experiment much more dramatic changes. And this figure explains why, because very quickly you start deviating from this nominally the intrinsic gold. You much earlier deviate from that. And if you put in impurities or have a slightly distinct system than pure gold, you actually see that kicking in much earlier.
Okay, thank you. Yeah, we don't have more questions. We will thank the speaker for a nice presentation. And the next invited talk and the last of this morning will be by Nicolas Reyden, who will talk about the spin-to-charge conversion using surface states of topological insulators. So you can start sharing your presentation.
So good morning. Thank you, Chairman. Thank you for the organizers for the nice conference organized in such conditions. So I hope you can see my screen now. Yes?
Yes.
Okay, perfect. So I will speak about spin-to-charge conversion using surface states of topological insulators. Initially, I planned to speak mostly about bismuth antimonide, but finally, the work didn't progress as much as I wanted, and so I will speak again about alpha-tin, and so the author list is a bit larger than initially than in the booklet. So I should also thank the financial support from the SkyTop European project and the French ANR Top-Prize project. It's a collaboration between several labs. So we at CNRS Thales we do transport, sputtering, characterization, and some analysis. And we also work with the Synchrotron Soleil, especially the Cassiope beamline for this project with Patrick Lefebvre. And also C2N for TEM analysis and MB growth, some of the MB growth by Aristide Lemaitre and Gilles Patriarche for the TEM analysis. Then I will show at the very end some terahertz measurements that were obtained at the Laboratoire Pierre-Hegrain in the group of Professor Dion. And then in the beginning, I will also show some spin pumping experiments that were obtained in the group of Florent Villa and Mathieu Jamet at SpinTech in Grenoble. So, well, as you've already heard a lot about spin orbitronics this morning, I will go very quickly through an introduction about spin orbitronics, and then I will discuss how the surface states of topological insulators can be used for spin-to-charge conversion. I will describe a bit the Cassiope beamline that allows us to grow the materials and directly check the band structure by RPS in situ. Then I will speak more about really spintronics and how I will concentrate in particular how to preserve the topological surface state in order to exploit them in spintronics. And I will concentrate on this for this point on the alpha-tin case. Then I will discuss a bit our more recent investigation of the surface states in bismuth antimonide. This first part was mostly done during the thesis of our student Quentin Barbedienne, who finished last year. And this part is the new thesis by Laetitia Barrington. So, well, now you've heard a lot about it already, but let me just remind you that conventional spintronics was based on exchange interaction, where mostly to get a spin polarized current, you get mostly spin polarized current from charge currents through ferromagnets. In spin orbitronics, you bring about new phenomena that are due to the spin orbit coupling. On one hand, you might stabilize new spin textures thanks to the Dzieloszynski-Moria interaction that emerge from the spin orbit coupling. And this allows you to, for example, stabilize magnetic skyrmions or fix domain wall chirality, which is very important for any type of, let's say, application of this type of textures. On the other hand, you can also perform a charge to spin conversion, either in bulk materials through the spin Hall effect that was brilliantly explained by Martin Kralhan just before, and at the interfaces that was also very well explained by Laurent Villa this morning, through the Dechstein effect, for example, at 3D topological insulator surface states or in Rashba interface states. So, well, one more time, when you speak about spin Hall effect, you pass, usually what you do is you pass a charge current, you accumulate spins at the edges of the spin Hall effect material. As it was described, well, this accumulation can be complicated if you have a few atomic layers only. But I will present, let's say, the standard easy diffusive model. Now, okay, you have some spin accumulation over a typical length that depends on the material. But you, in a, let's say, static configuration where you have a constant current in the system, then you don't have any more spin current. You just have a transient spin current to accumulate the spins on the edges. Now you need a spin layer, typically a ferromagnetic layer, in order to generate a spin current towards the ferromagnetic layer. And then there are many things that can happen at the interface. It was again very well described. So finally, well, you have a spin current, but some of the spins are lost at the interface. And usually the efficiency is given by this spin Hall angle. In this case, where I apply a charge current and I generate a spin current, it's the ratio between the spin current over the charge current. And this gives you a number. But this number, of course, in an experiment, is an effective number that depends on all the details of the interface and so on. So I just want to remark here that if you want to fix the current, not the current density, then to have an optimum current, a spin current density, you need a thickness of the spin Hall effect material that is about the spin diffusion length. I will come back on this later to compare with the surface states. So finally, thanks to this spin current, of course, you can generate spin torque on the ferromagnetic layer and control maybe the magnetization of the ferromagnetic layer. So this was demonstrated already in 2012 for platinum, tantalum, cobalt iron boron. So it was described just in the previous talk how tantalum can be very efficient or can have a very large spin Hall angle. Also in platinum cobalt, where by Miron and co-workers, also maybe the alumina take a role in 2011. So both these examples shows that you can control, you can switch the magnetization between two states. Here the magnetization is out of plane, you switch from MZ1 -1, and here it's in plane, you switch between these two different directions. So this has implications if you want for applications. So for example, so 3-terminal magnetic random access memories, for magnetic racetracks and so on. Now, the current densities that are used are typically a fraction or a few teraamp per meter square. So it's very huge current densities. And maybe we need to find new approach to find more efficient ways to control the magnetization. And that might be through the surface states of, for example, topological insulator. Indeed, it was published already in 2014, for example, in this study, that with a topological insulator, you can manipulate the magnetization state of a ferromagnetic layer on top. There are several examples. including one for bismuth antimonide in 2018, that shows that you can finally switch the ferromagnet with current densities that are typically orders of magnitude lower than what you get in metallic systems. Note, on the other hand, that here the metals are, the ferromagnets are maybe not conventional hard magnets. Now, how do you use these topological insulators to produce these spin current? So, well, let's assume you have here B is a topological insulator, A is a trivial insulator or vacuum. Then you have band crossing at the interface, and you have a Dirac-Cohn linear dispersion that is typically presented here. That results from this topological insulator Hamiltonian, where you have here the spin, the momentum, and here Z is the direction perpendicular to the interface. So this Hamiltonian means that you have a spin momentum locking. You minimize the energy when the spins are orthogonal to the K vector. So these, well, if you take this Dirac-Cohn and you take a cross section for Kx equals 0, what you get are two lines. And when they cross, you have the Dirac point. And these two lines have an opposite spin polarization. And this is observable experimentally using a spin resolved angle resolved photoemission spectroscopy. And this is an example of what has been obtained in alpha-tin system at the Cassiope beamline by Otsubo and co-workers. So the color code here codes the spin polarization, and you see that you get such conical dispersion with two branches with opposite spins. Now, quite interestingly, with these systems, if you manage to change the position of the Fermi level compared to the Dirac point, then you change the helicity of the Fermi level. So here it's going, let's say from top, it's going clockwise, bottom is getting counterclockwise. So this is important for the following thing, is that you can use these surface states to convert spin to charge currents. So let's take the Fermi contour of a topological insulator. So you have spins locked around the contour, orthogonal to the K vector. And what happens when you apply a charge current is that mostly you will shift the Fermi contour, and this will result in the fact that here you have more K values that are along Kx, and at the end you accumulate some spin along the Y direction. So this is so-called the Edelstein effect. You can do also the opposite, the complementary, let's say, you inject a spin current. So let's say you inject spins along Y direction. That means that you will populate mostly the Kx, positive Kx values, and that results in a charge current. So similarly to the spin Hall angle, we can define a parameter that is the ratio between the charge current that you generate over the spin current that you inject. This is the, well, inverse Edelstein effect lens. But here the difference with the spin Hall effect is that you have a 2D system here. So the charge current occurs in a two-dimensional system. And so its units are amp per meter, while the spin current is injected from the ferromagnet. It's a 3D spin current. And so you have at the end a parameter that describes the efficiency of the conversion that has units of meters. Similarly, for the direct effect, you have the ratio between the 3D spin current and over the 2D charge current, and this gives rise to an inverse of a lens. Unlike the spin Hall effect, this inverse Edelstein effect lens is not equal to 1 over the Edelstein effect inverse lens. This is discussed in this paper. So now, if you want to use these surface states for spintronics, what you need is probably thin films on an insulating substrate, and because you need to limit any current shunt, including in the ferromagnet. In fact, one of the, let's say, issue with the surface states is that typically their sheet resistance is several, maybe hundred of ohm per square, While if you consider platinum with a thickness of a few diffusion lengths, spin diffusion lengths, you will get only a few ohms per meter. So yeah, the shunt current is a problem when you want to make a device. And of course, if you want to make use of surface states, you need to connect them without destroying the surface states. And in particular, if you deposit a ferromagnet on top of your topological insulator, what is happening? Do you keep the conical dispersion or not? And there are also questions about the interface transparency that we have already discussed. So we studied, among others, two topological insulators, the alpha phase of tin or gray tin, and the bismuth antimonide with some concentration of antimony between 10 and 30%. They were both predicted to be topological insulators by Fu and Kane in 2007. In order to study how the surface states evolves and so on, we need ARPES to access to the band structure, and also a growth facility in order to deposit layer by layer, let's say the top electrode, for example. So this we can find at the Cassiope beamline at 7 synchrotron. So this is a poor resolution picture, sorry for this, of the Cassiope beamline end station. And you see here the molecular beam epitaxy chamber where we can prepare the substrate and analyze them and then grow the films. It's connected through vacuum to the ARPES chamber that is behind there. There is also a spin resolve photoemission spectroscopy chamber where Otsubo could do the image of the spin polarization in the alpha tin. And okay, so this is the top view. Here you have the ARPES chamber, the MBE growth chamber, and essentially what you do is that you take light from the synchrotron ring, you shine it on your sample, and you get an electron out, and with a detector and an analyzer, you will measure its energy and its momentum. This way you can reconstruct the band structure. Just a detail about the MBE growth chamber. So there are two Knudsen cells that allows us to deposit, for example, the bismuth antimonide by co-evaporation, or the tin also by evaporation. And then we have several targets that we can evaporate by e-beam evaporation, especially the metals, including the ferromagnet. So let me now switch to the case of alpha tin. So this is a typical map that we get for the tin that we deposit in this chamber. And you can see that you have clearly this Dirac cone, well visible here. You have the Fermi energy that is around here, and a Dirac point that is slightly below. Now, if you deposit a very thin layer of aluminum, only one atomic layer, you see that you can still see the cone, but now it seems that the Dirac point is above the Fermi level. If you oxide your aluminum, you still see the Dirac cone behind this layer. And if you deposit silver, you can also, even though the layer is quite thick, you can still see the Dirac cone. So in all these cases, it seems that we can preserve the Dirac cone and hence probably the spin momentum locking. So that means that the alpha tin is still useful for spintronics. On the contrary, if you try to grow MGO, we see that very soon we don't observe anymore the Dirac cone. And this is due to the fact that, in fact, we oxide the tin layer. Similarly, if we deposit directly iron on top, we also lose the track of the cone. So probably in these last two cases, we will not be able to beneficiate from the spin momentum locking because there are no more Dirac cone. Just to come back on the fact that the Fermi level seems to change, indeed, the blue points here show the Fermi level minus the Dirac point energy is a function of the thickness of the alpha tin. So there is no really dependence, but we always have an N-type system. And when we cap with silver, we see that we keep this N-type system. But when we deposit aluminum or aluminum oxide, as I showed you, it seems that the Fermi level goes below the Dirac point, and then we have a p-type conduction. So it looks very interesting for spintronics because you could imagine making a p-n junction. You can invert the spin texture, and so you invert in principle the spin to charge conversion, and so on. But okay, so how can we measure this spin to charge conversion? So in the case of silver, we used spin pumping. So we did some, let's say, test experiments with the substrate and the iron and no alpha-tin. Of course, we don't see nothing. When you have iron in direct contact with the alpha-tin, we also do not see no conversion. And this is attributed to the fact that, well, we don't see anymore the cone. So probably we destroy the band structure of the alpha-tin. But finally, when we use a silver interlayer, we preserve the surface states. And indeed, we see that we have a large spin to charge conversion. So I didn't describe too much these spin pumping experiments because it's the same experiment that was described by Laurent Villa this morning. So the inverse Sandstein effect here is only observed for samples with a preserved Dirac cone. Now, how good is it? So the spin charge conversion here is about 2.1 nanometer using the silver spacer. And we can compare it with the silver bismuth interface that was presented this morning, 0.3 nanometer, or the lanthanum aluminate strontium titanate interface, where you can modulate the Rashba effect and you get a length between 2 and -6 nanometer. And how does it compare now to bulk materials? So there, you cannot directly compare the spin hole angle and this length. So what we do is that we look for the, let's say, ideal length that correspond to the spin hole angle times the spin diffusion length. So at these conditions, that's when you convert, let's say, more efficiently a given current. And this length is corresponding to less than half a nanometer. So from this point of view, it seems that the alpha-tin surface states is very efficient to convert charge current into spin current or reciprocal. Now, what controls this length? Can we go even higher? So in principle, this length is just the Fermi velocity that we measure directly by ARPES times the carrier lifetime. And because we measure this length, we deduce a carrier lifetime of about 3.7 femtoseconds. So that seems to be a bit short lifetime for these surface states, especially if we look at optical experiments where it can reach 10 picoseconds. So, okay, maybe these optical experiments are not completely comparable with what we do with transport, but nevertheless, we could expect maybe larger lifetime. And what can we do better to get longer lifetime? So maybe what we think is that this reduced lifetime is due to the hybridization of the state with the silver state. So maybe using an insulating barrier would allows you to get longer lifetime. And that's in fact what we did when we capped our system with aluminum oxide. But when we try to measure spin pumping effect, we don't see no effect. So what is happening? In fact, if you look at the standard Hall effect, I'm sorry, there are no scale here, but it's between -9 and 9 Tesla, I guess. So you see that you have this S shape that is typical for multiband transport. And in fact, we have a huge contribution from a bulk band, which does not convert the spins, but that absorb the spin current. And that way, we explain that we do not see the spin to charge conversion. But the carrier density that we can infer from the high mobility band, due to the fact that they are Shubnikov-Duras oscillation, they correspond to the surface that we observe by ARPES. So somehow we can check that indeed these surface states survives, especially if you look also at the position of the maxima and minima as a function of 1 over the field, we find something that is corresponding to a Dirac type of carriers. So it really corresponds to the direct cone. The problem is that we have this shunting of the effect by the bulk band. From the conductivity measurements, we can estimate a lifetime of about 60 femtoseconds. So from this point of view, we managed to improve the situation. But okay, as I said, we have the bulk band. And this is related, in fact, to the fact that the gap in the alpha tin is only a few tenths of millieV, a few times 10 millieV, and well, it's related also to the strain, and so we cannot really control this, and we decided to switch to another system, the bismuth antimonide. So this one, as I said at the beginning, it was also predicted in 2007 by Fu and Kane. And the same year also by Murakami. The surface state, let's say, depends on the doping. X here is the atomic fraction of antimony. And so you have a band crossing, and you have a part where you have a gap that opens, and you have the topological insulator. This was observed already 1 year later by Xie and co-workers. And 1 more year later, people observed in the cleaved bulk materials that you can have, that these surface states are in fact spin polarized. And so that's exactly, again, like in the alpha tin, what you want to have in order to be able to do spintronics. But that's not enough. You also require to have thin films. So are the properties preserved in thin films? In fact, Benya and co-workers showed that it was the case in 2015. You need an insulating substrate to avoid the shunting in the substrate, and you need to preserve again the surface states after the capping. So back to Cassiope beamline, where this time we do these co-evaporation of bismuth and antimony, and we tried the different substrates. So the first one we tried was because of the small mismatch, 1.5% only, and you see very nice atomic force microscopy image of the surface. But the problem is that indium antimonide has a very small gap, and you have a large shunting, especially at room temperature. Moreover, we tried to make thin films of indium antimonide and gallium arsenide in order to reduce the thickness of indium antimonide and its shunting, but then you may have some interface with Rashba effects with gallium arsenide, and so it's too complicated. And finally, we give up with this substrate. We also considered the barium fluoride substrate. Here, the mismatch is a bit larger, but still reasonable. The advantage is that the band gap is huge, 11 electron volts. So it's an excellent insulator, even way above room temperature. But ARPES was nearly impossible due to charging effect. In fact, we were depositing grids of metals, for example, on the substrate in order to follow the growth, but it was impossible. So finally, we end up with the silicon 111, where the mismatch is huge, but you can use a highly resistive silicon that is good enough for application even at room temperature. So how is it growing on this silicon? In fact, if you look at the X-ray diffraction, it looks very good, because here you see the diffractogram where you have the peak of the silicon and the peaks of the OOL bismuth antimonide, plus maybe 2 oxides, because this one was not fully capped. If you look at this peak, you see finite side fringes. And if you look at the rocking curve of this peak compared to the substrate, you find that it's mostly strained, and you have maybe a few dislocations, but the films looks very good. So how is it possible with 15% mismatch? In fact, scanning transmission electron microscopy can help us to understand this. So here you see a cross-section in a high angular dark field, where the light atoms are very dark and heavy atoms very bright. So maybe you don't see nothing on your screen. So I asked Leticia Barrington to redo the color scale in order to show each atom. So here you can see already the columns of atoms in silicon and in bismuth antimonide, and you can see that they fit exactly what you expect from this material. And you don't see large dislocation or things like that. So what is happening at the interface, in fact, it was quite funny to see that you have, say, fractional matching. So for 6 bismuth antimonide, you have 7 layers of silicon. Well, it's not super visible here, but that's that series of atoms is exactly the one that is shown here, and you see that we can fit well the position of the atoms. So bismuth antimonide at the end is only weakly strained. ARPES now reveals that we have the surface states that we expect. We find the same surface state as in bulk or in other film studies, with a surface state here and another one here. Okay. Now we could also confirm that around the gamma point, these surface states are indeed two-dimensional because they do not disperse in Z. This is possible thanks to the fact that in the synchrotron we can change the energy of the incoming light. So to be continued, we are looking for the signature of the topological spin surface state. Topological surface state in the transport measurements. We perform some spin pumping in the direction magnetic resistance, spin orbit torque with 2 omega measurements, and so on. Of course, distinguishing surface state from Bose state is central. Now I think I don't have much more time to describe all this, and finally they are all very preliminary. So I would just like to show the signature of these topological surface states in the terahertz regime. So it's we look at terahertz emission, which is a nice probe for the spin-to-charge conversion. It's an all-optical technique where you shine a pulse, femtosecond pulse of near-infrared light that hit your ferromagnet that will generate some heat wave or something like that. That allows you to let's say, produce a spin current that is then converted into a charge current that generate then this terahertz pulse that we can observe. So it can be generated by inverse pinhole effect for the case of cobalt platinum that performs very well. It's one of the materials that is known to work well for this terahertz conversion. And you see that cobalt bismuth, the interface between cobalt and bismuth antimonide works very well as well. And this does not depend on the substrate. So I showed you the silicon bismuth antimonide case, but barium fluoride, even so we cannot see the ARPES if we assume that the bismuth antimonide grows the same way than on silicon. We assume that they have the same topological surface states, and indeed we see the same very large conversion. Unlike the alpha-tin case, when we deposit aluminum in between the bismuth antimonide and cobalt, the interface here is very much degraded. The interface is bad, and you don't see no conversion. In fact, the curve is well, undistinguishable here in the middle. On the contrary, when we grow, and we are a bit surprised about this, cobalt directly on top of bismuth antimonide, the interface is clean and we have no intermixing. So with this, let's say cobalt bismuth antimonide, it seems that we can directly use the surface states at this interface in direct contact with the ferromagnets. So in conclusion, I showed you that the alpha-tin is probably an interesting system. It's a simple elemental material with potential control of the spin helicity by changing the position of the Fermi energy compared to the Dirac point by using different coupling layers. But it needs an insulating substrate. It has a very small gap. And so you have a lot of shunt in the bulk of the tin itself. And you need then a low temperature. Bismuth antimonide shows promising properties. Maybe you can adjust these properties by antimony concentration. It was previously demonstrated by other authors that by Kang et al. That you can do spin torque with it, and we just showed that you can produce large terahertz emission. And with this, I thank you for your attention.
Thank you, Nicolas, for the very nice talk on using the surface states of the topological insulators for spintronics. So we have the first question from Felix Casanova. So he asks, why do you choose the 8515 in bismuth and antimonide? How much does the bulk conduct?
So this is, I would say, still under investigation. We did several concentrations. Let me see. And indeed, there are still large effects from the bulk. I don't have the resistivity curve, but you see that it goes first up and then it makes a bump. So that means that at room temperature, you still have quite a lot of bulk contribution. Well, it's always the problem with these things. Hopefully, at some point, we might maybe either add some dopants in the system to control the position of the gap, or maybe even use some gate effect. But then how to combine gate and spin pumping or spin charge conversion is not easy. So we studied between 3% and 30%, let's say, but well, I just showed 15% for simplicity, but well, it's still under investigation, I would say.
Okay, good, thank you. So the second question is from Marcos Guimaraes. He's asking whether, so is the disappearance of the Dirac-Cohn due to material intermixing disorder or doping?
Well, from what I see, well, in the case of MgO, it's clearly a problem of, okay, at least we can see by X-ray absorption spectroscopy that the tin is oxidized. So maybe the cone is then hidden below this oxide layer of the tin. This we cannot say. What we see at least is that we don't observe nothing, then no signature of the Dirac cone experimentally. For the case of iron, it's also possible that it might be also some, how to say, some intermixing or some alloying of the system indeed. We deposit at room temperature, but still for this very, let's say, the liquefaction point temperature for tin is very low also. So I guess chemical reaction can occur, yes.
Okay, thank you. Next question is from Emmanuel Martinez. He asks, how could be qualitatively understood the displacement of Dirac cones as a function of capping? And is it related to the polar electric field generated along Z?
So, frankly, I'm not sure. For me, it was more a question of just, what is the name? Work function difference, but maybe there are also this type of phenomena. It would be interesting, in fact.
Okay. So we have a question from Ruben Garcia. Why did you choose bismuth and antimonide over other well-known 3D topological insulators such as bismuth selenide or bismuth telluride?
Yeah, what would be the no? Well, it's a good question. This one was not so much studied. Well, there were a few studies. When we started to do this, the paper on the spin torque was not out yet. And so we thought, okay, this would be interesting. And also coming back to the ones predicted by Fouilken in 2007 was kind of fun. But no, I don't have a good, a very objective reason. But in bismuth, BI2, T3, and so on, there are so many people. And also the problem is always the growth for us because we don't have the MB chamber at home. So we use either at C2N or at Soleil. And so, well, we don't have so much time to develop the materials either.
Okay, thank you. And also he asked, Ruben Garcia asked, whether, well, I guess iron breaks time reveals asymmetry.
Yeah, that was our idea that maybe these topological insulator surface states are supposed to be well, resilient to any kind of disorder, except if it is a magnetic disorder. And indeed, if you put some ferromagnetic atom inside the system, you might kill the surface states. That's why also we were a bit surprised that it works so well for this cobalt in direct contact with bismuth antimonide. But okay, maybe there are some details on the interface. I don't know.
Okay, thank you. Yeah, we don't have more questions, then we will. So the first contributed talk of this morning is from Jose Garcia, who will talk about charge to spin conversion in low symmetry topological materials. So
hello.
You can start sharing the presentation.
All right. Do you see the presentation?
Yes. Yes.
All right. So thank you very much to all of you for allowing me to present my work on exotic spin transport in two-dimensional materials. This work is a collaboration between the ICN2 in Barcelona, the University of Grenoble in France, and the University of Singapore. And also, I would like to thank the organizers for managing to transform an online event, a presential event, into an online event. I know that it's probably a lot of work and there was a little of time, so thank you, the organizers. So I know that everyone here knows about spintronics, especially the previous talk made a very good introduction, but because this is going to be recorded, I'm going to go very fast to the motivation of our field. So we all know that all electronic devices work by the movement of electrons, and this movement of electrons generates a current. The problem is that when the electrons collide in a material, then this current hits the material, and this is the main principle behind resistive heaters. And this dissipates some power. And in a world where we have so much devices, this power dissipation is starting to be a burden. But if you know something about quantum mechanics, you know that the electron also have an additional property, which is the spin, and you can actually move the spin without moving the electrons. Basically, this allows for an efficient way to transport information without any dissipation. And also, if you know that this spin is related to a magnetic moment, it's basically a magnetic moment, then you can also envision the capability of manipulate magnets through these spin currents. So the catch here is, how do you create these spin currents? We saw already different ways. You can do a spin injection, you can do you can use the Rasch-Wallerstein effect, or you can use the spin Hall effect that was mentioned in the previous talk. And in this talk, I'm going to focus mostly on the spin Hall effect. So in the spin Hall effect, you basically pass a charge to a material, and this charge generates a perpendicular spin current with the polarization of the spin in some direction. And to quantify this phenomenon, this phenomenon is driven by spin-orbit coupling. To quantify this phenomenon, you have to you can compute or determine the spin Hall conductivity that tells you basically how much spin do you create by the application of an electric field, or you can also determine the spin Hall angle, which basically tells you how much spin Hall conductivity do you generate per units of charge current. So this is basically a dimensional conversion efficiency parameter. And the good thing is that it can be larger than 100%. So also in real life, these electrons must lose the spin information while moving. So you want that this figure of merit called the spin relaxation length to be very large. So the question is, can we have a spin to charge the conversion, a large spin to charge conversion, and also a long spin relaxation length? And the question is, yes, there is this phenomenon called this quantum spin Hall effect, where the electron travels along the edges of a material, and they are completely insensitive to certain kind of disorder and scattering. So this phenomenon was difficult to realize, and it was a very good prediction that you can achieve this phenomenon in 2014 by considering tungsten telluride in the 1T phase. And then the realization of this effect was given in was then achieved in 2017. First, by doing some capacitance measurements that determined that there was indeed conductive edge states. And then in 2018, there was a purely electrical transport measurements that point out to the presence of this topological state at the edge of the device, and they actually measure how much the quantum of conductance that you expect for this material. So the problem is that these guys did this, this experimental group did this electrically, but it's not a problem. They actually measured the effect. But in order to use this spin, you need to determine the spin characterization. And this was done recently by the group of Felix Casanova and the group of Kim-Ping Long on a different material, but that also present these low symmetries, this 1D phase. And what they basically determined, or what basically found, is that you have multi-directional spin-to-charge conversion, and also large spin-to-charge, large spin relaxation length that can go over the micrometer scale. So this was very surprising, since it's not usual that you have both spin-to-charge large spin-to-charge conversion and long spin relaxation lengths. So I'm going to take advantage of this nice figure of the paper of Felix to explain you why is that these in materials are interesting. So typically what happens is that in two-dimensional material with high symmetry, you have typically two orthogonal mirror planes, and these two orthogonal mirror planes forces the charge current, spin current, and the spin polarization of the spin current to be orthogonal between each other. But as you reduce these symmetry planes, you allow for different direction of the polarization. As you can see also in the spin conductivity, this is in the spin conductivity elements that are allowed due to this particular layer group. So if you go to two-dimensional material, so you take this 3D bulk material and you lower it to two dimensions, then what you find is that all the vertical elements are forbidden, and that you have only two directions allow for the spin current, which are perpendicular to the charge current. Also, we did a band structure calculation, and we found that this material in this particular phase, geometrical phase, has two charge pockets that crosses the Fermi level located at two special points, Q and Q prime, that are related by time reversal symmetry. So using the DFT calculation, we built a model and we parameterized the model using the band structure. And what we found is something interesting. We found that around this Q point, which is the important point for the transport calculation, you have this spin texture here that has a very similar shape to the spin texture that you expect for spin momentum locking. But when you look at the actual spin texture that is here, you see something curious, which is a persistent spin texture. And this is a consequence of the own nature of the Q point and also of the singular nature of the spin texture. So this is a consequence of the low symmetry of the material. And we'll see that this persistent spin texture or constant spin texture around Q is very important. So, and then what we see is that this particular point will be also negligible because this Q point actually lays on the KY equals 0 axis. So to characterize this model, we consider we take this model and we then try to determine the spin properties. So we built a non-local spin valve using our modeling tool Quant, and we actually develop a theory that allows for considering the whole range of a spin-orbit coupling, taking into account the contacts, and all of this is given in this particular reference. That is what we use. So to tell you more or less, for those who do not know what is a non-local spin valve, you pass a current from 2 to 1. This contact at 2 is a ferromagnetic contact, so you build a spin accumulation in your substrate. This spin accumulation diffuses a spin current that you measure from 3 to 4, and by measuring the distance dependent, you can get the spin relaxation length. So we did this in this particular material, and what we found is that there is an isotropic spin relaxation, and the spins pointing in the y direction. So the spin that I basically inject a spin in the y direction and see how it relaxes to distance that are over hundreds of nanometers. While the spin in Z and the spin in X relaxes very fast. In particular, the spin in X basically relaxes immediately. And we also found something that is very interesting, that when you move to the Fermi level towards the bottom of this conduction band, you see that the spin relaxation length increases, and it can increase even 3 times. So, so why is this? And for this, you have to remember a little bit one of the mechanisms for spin relaxation, and that is that if you have spin momentum locking or spin orbit coupling in general, and your electron is moving with a particular momentum and then it scatters due to disorder, then this effective magnetic field due to the spin orbit coupling will change. And then if this happens a lot, the electron will feel a random magnetic field and will lose its spin information. But if you have a persistent spin texture and your spin is aligned to the direction of your spin texture, then you scatter and you basically feel the same magnetic field that won't make your electrons to relax. So basically, in this case, the only thing that could happen is this dephasing. So in this case, in this particular case, you see that the spin texture is pointing primarily into the y direction. It's basically y and z like this. And then because it's aligned in the y direction, when you put the spins, or mostly aligned in the y direction, when you put the spin along that direction, the spin survives more. And because this is the YC plane, when you put the electrons in the X direction, it relaxes immediately because it feels a complete perpendicular magnetic field. What we did then is to try to determine the spin Hall effect. And by doing this, what we did is to put to create a 2-terminal device, pass a current in one direction, and then measure the spin accumulation using quant again. And then by looking at the spin accumulation, what we saw is that there is an accumulation in the y direction, there is an accumulation in the z direction, and 0 accumulation in the x direction, as expected by the symmetries of the material, and in a similar way that some people do through experiments. And then here you can see a quote that basically average over the whole y distance. You see that we have a theory to actually extract the spin Hall angle, but basically what you can see here is that the spin Hall angle from the y direction and x direction is opposite and is larger in the y direction. So we wanted to understand, because we have this large spin Hall conductivity, and we also have a reasonable long spin relaxation length of 100 nanometers. It's not 1 micrometer, probably due to the low dimensionality, or in reality we still don't know why we have some 1 order of magnitude spin relaxation length, but the spin relaxation length is still quite high when you understand that using our measurement we obtain this spin Hall angle that can go even to 80%. Okay, so to understand this, we actually say, well, this is a quantum spin Hall insulating material. We think that it could be have some topological origin. So what we did is we compute the spin Hall conductivity due to only the Berry curvature, and we compare that with the result that we obtained in a device where basically we're doing exactly what the experimentalists can do. It's just a device with two terminals, and we measure the accumulation. And we found that the agreement was very good. The Berry curvature and the device simulation matches very well, which indicates that the spin Hall angle probably has a topological origin. And this could also make you understand that when you go close to the Berry curvature, if this is actually a quantum spin Hall insulating state, you expect that the spin relaxation length to go to very large values, as I mentioned before. So the problem is, we say, well, let's try to compute the spin Hall angle and see if we can see quantum spin Hall state. And the problem is that molybdenum telluride has a band that closes the gap and won't allow you to see this quantum spin Hall insulating state. But tungsten telluride does not have this band. So we then make another study on tungsten telluride, which basically is very similar, and the model that we developed fit well both the structure, and this is the result that we obtained. First, the spin texture is different. In this case, the spin texture is more in the Z direction than in the Y direction, but you have also a persistent spin texture around the Q point. And this angle, in this particular case, I'm putting the angle below because it's important, is minus 56 degrees. And can be obtained by the spin-orbit coupling parameters of the model, okay? And this is maybe the main result of my presentation, and is that when we take this model, we did Kubo calculation, full Kubo calculation, not just Berry curvature every time. We obtained that at the gap of tungsten telluride, the system becomes a quantum spin Hall insulator. But let me guide you through this slide here. What we have is that what happened is that we measure the spin aligned in X, in Y, and Z. The spin in X is 0, as determined by the symmetry. But we found a spin Hall conductivity that is a not a non-quantized value in the Y direction and the Z direction that follows a similar relation that you expect from the spin texture, which is that the Z direction is larger than the Y direction. So we say, well, this is maybe what we have is a quantum spin Hall insulated state where the spin is tilted. So basically, we compute the norm, and actually we found that this norm of the spin polarization is 2, which means that there are 2 counterpropagating edge states, and that this is in fact a spin current that is tilted. So we take the model, we tilt it by this lambda parameter, by using this spin orbit coupling parameter, which is 56 degrees, negative 56 degrees, and we also take a similar curve as the black one. So this result tells us that the low symmetry of the tungsten telluride and probably the low symmetry of MOTE2 allows for a quantum spin Hall insulating state that has this particular nice thing that is tilted, and which means that you are not longer constrained to the typical picture where the spin is perpendicular to the plane of the 2D material. And because this tilting is depending on the spin orbit coupling parameters, you can imagine that you can tune it by changing the electronic environment, for instance, by changing the substrate. This value will change, and you can maybe put it completely out of plane or completely in plane. Finally, we test that if this state were topologically protected, and for that we did purely resistant device inspiring what Pablo Jarrillo did in his Nature paper, and we put some very strong some very strong disorder, which in this case is Anderson disorder of the order of 1 eV, and typically the disorder in the experiment is of the order of 100 MeV in the worst case scenario. And we see that the effect survives even to this strong disorder. If we reduce the disorder, the plateau becomes larger and wider. So this indeed is another indication that these are topologically protected states. And here are the conclusions. First, the monolayer TMDs in the 1TD phase can sustain this huge multidirectional spin Hall effect and simultaneously a long spin relaxation length. Part of this origin is due to this persistent spin texture. Another part is due to this hotspot of Berry curvature at the Q point. And these two things leads to this canted quantum spin Hall effect, which is allowed by low symmetry and is driven by this low symmetry. So thank you very much.
Thank you for the nice talk. So I will start going through the questions in the chat. So be reminded that you can ask through the chat, and as well as also interact with the speaker if you use the raise button option in the Zoom. So the first question is from Marcos Guimaraes. He asks, what do you expect for the spin Hall effect for few layer molybdenum telluride, tungsten telluride?
So we did a calculation for these materials. We have this material more demanding, and we don't have a model, so we have calculation on a Vanier level. And what we found is that you expect to have something similar, but because you have more layers, this nice gap that you have in the monolayer case is not present there. So you can expect to have this quantum spin Hall isolating state in combination with box state, which is a pity because then through scattering they can mix and you lose some of this their topological protection.
Okay, thank you. Yeah, he says Nerea Antoso ask, thank you, Hugo, for the nice talk. I'm wondering if the results in the monolayer transition metal decalcogenides can also be applied to few layers.
So this is more or less the same question, I'm guessing. Yes and no. I mean, there is something that is still not well understood, which is when you do the calculation for monolayer case, you see a very short spin relaxation length compared to the current measurement by Singapore. In the current measurement by Singapore, you have 1 micrometer spin relaxation length. I have, in the best case scenario, 100 nanometer. So it's not clear what improves the spin relaxation when you go from one monolayer to many layers. The spin Hall signal is probably going to be, for MOT2, is probably going to be very similar because the band that moves when you have multi layers is there already, is already closing the gap. But there is not a clear understanding on the spin relaxation part. The spin to charge conversion is probably going to be very similar.
Also, on the fact, for instance, in the spin absorption experiment, you have a vertical stack, so it's not the same the same kind of layered structure, and you would have effects from going the spins in transversal instead of flowing, for instance, in the plane of the layer, right?
Yeah, and in many cases, some of the effect is attributed to this vertical transport, but at least in the Singapore experiment, this is a lateral device, so this 1 micrometer scale is a lateral transport. So it's in that particular case, it's a very long relaxation length.
Yeah, thank you. So Marcos Guimaraes would like to make you a question.
Yeah, it's easier or nicer also with the voice, I think. Thanks for the talk. Did you also do this the calculations for the tungsten ditelluride that you show the spin Hall effect, or well, the spin the charge to spin conversion in the device geometry that you visualize the spin accumulation at the edges, similar to what you showed for
this one, right?
The molybdenum telluride, yeah. Did you also do that, but for tungsten telluride as well?
Yes, and then what happened is that you see a switch on the Y and Z. So Y is going to be, because of the convention that we use, it changed from blue to red to blue. And also this panel here that shows that Y is in 1 and Z is in 0.5. In this other case, it shows the opposite trends. Actually, there is always this, for this plot and for the spin relaxation length and for the quantum spin Hall insulating state, you can always trace the relative value of the spin polarization to the spin texture. And this is due to the fact that the spin texture is a persistent spin texture. So in MOT2, the spin texture is in Y direction, mostly. So you get everything in Y direction is larger, and in tungsten telluride is in Z direction mostly. So you get everything in the Z direction is high.
Can I ask another question?
Yeah, sure one, please. Yeah, we are running out of time.
Sorry. As you go for a few layers, I can imagine that the recovery of inversion symmetry for the molybdenum telluride will have a strong impact also on the spin texture that you get, right? While for the tungsten telluride, you don't have the inversion symmetry. So I think that there should have a very, very different behavior as you increase the number of layers.
So actually, we have a parameter in the model. So you mean the out-of-plane inversion symmetry because there is this glide.
Yeah.
So we have in the model, we have a parameter that take that into account. Let's see if I can go there. So this eta parameter here is a parameter that basically break this inversion symmetry. In the model, we can turn it to 0 and turn it to some small value. And what happened is that there is a splitting, but we see basically no change in any of this behavior that I showed. So there is a tiny splitting. Actually, we also made some calculations that are not present here with the substrate, without the substrate, with the multi-layer. And we don't see that this inversion symmetry changes this particular phenomenology.
Okay, thank you. With this, I'm afraid that we are running out of time. So thank you, Jose, for the nice talk. And we move to the next speaker, who is Peter Mack, who will talk about charge-to-spin conversion in graphene bismuth telluride bromer heterostructures. So please, you can start sharing the screen.
So I hope you can see my screen and everything is fine. So thanks again for the opportunity to present our work. First, I would put a bit of context. So, I mean, there was not much talked about graphene or two-dimensional materials today alone yet, except like the previous talk. So I would like to mention why we are interested in these materials. So, I mean, everyone knows why graphene is a wonderful material, you know, the relativic band structure. It's quite easy to work with. So you can put superconducting contacts, ferromagnetic contacts. These were quite reliable. It's not air sensitive. You can make gapless PN interface. And I think the wonderful thing is shown here that you can just engineer the band structure of graphene by stacking them on two different materials on top of each other. You can induce spin orbit interaction exchange or superconducting proximity effect, or there will be a full mini colloquy about, you know, like Moiré structures, which you can use. From spintronics point of view, it's interesting because it's a good spin channel. For example, you can have long spin relaxation times. There are just some papers collected, but it's not exclusive to LICS. So, you know, you can have spin relaxation lengths over several tens of microns. You can have large polarization. This is because there's no spin orbit interaction and there are not many nuclear spins in graphene. So some challenges which we were addressing, some of us in the recent years, is to combine high quality graphene with spin valves, to fabricate reliable tunnel barriers, to induce spin orbit interaction into graphene, or to try to control electrical spin polarization in these structures. And some of the works I just touch upon. So, for example, we investigated that how boron rhytide can be used as a tunnel barrier for these structures. Or if you want to go another way to avoid conductance mismatch, you can try to use dynamical spin pumping. So these are some works which are connected to the field. And to go more in the direction which I want to talk about, one other work where we are very involved or where we did something is to try to induce spin orbit interaction in graphene Here, the idea was to induce spin-orbit interaction by placing graphene on tungsten selenide. And what we have shown, similarly to a lot of works in the literature, that you can induce spin-orbit interaction in graphene. What we have found is that there's a sizable Rajba and Valley-Zeeman spin-orbit interaction, which leads to large spin relaxation and isotropy. So this work was also a collaboration with the previous speaker, and similar measurements have been done in spin-valve devices. So this was like 2-3 years now ago. And since then, this field started to explode. People have figured out that you can induce spin-orbit interaction in graphene. Then you can alone use the graphene to generate, for example, spin currents via spin to charge conversion effects. So this is one way where there's a lot of nice works from the group of Sergio Valenzo, Bart van Wees, Saroj, or the next from Felix's group. I guess the next talk will be something about this. What I will talk about is a tiny bit different. So what we have done is that we have generated spin currents in a bulk material in bismuth tellurbromide, and we have used this spin current generated in the bulk material to inject into graphene. So we didn't rely on the proximity effect in this case, but this was an effect in the bulk material. And this was recently published in this work. So why we have chosen bismuth tellurbromide, which was the one where we generated the spin current, is I think it's quite easy to motivate. It has a really large Rajba spin orbit interaction. This comes from the fact that it's with heavy bismuth atoms, which are sandwiched in a polar environment between tellur and bromide atoms. So because of the broken inversion symmetry, there's a large Rajba splittling, which is now on the order of 40 millieV in this case. So this is really, they call it giant sometimes. So here is the Rajba band structure again shown. This you have seen once or twice today already. Just the main feature, if you are at really high energy, there are two Fermi surfaces. In both you have spin locked to the momentum. The chirality is opposite. The spin is winding always perpendicular to the momentum. And at zero magnetic or electric field, there's zero spin polarization in this material. However, as already was shown today, if you apply an electric field, what happens in this material that you shift the occupation of the bands. This is also shown in the 3D image here. So what happens, for example, if you look the outer circle, that at positive momentum, you will have more downspins, whereas negative momentum, you will have less upspins because the circle is shifted in this direction. So by applying an electric field, you generate a spin polarization, which is perpendicular to the electric field. And though there are two Fermi surfaces here, this effect does not disappear. So the inner Fermi surface is smaller, whereas the outer is larger. So there's still finite polarization remaining at the end. So this is also called spin galvanic effect. With the electric field, now you can determine the direction of the spin polarization, and the strength is determined by, for example, Rajba coefficient, density, and so on. I will come back to this. So to show how we did our measurement, this is like the setup which we have used. So we have a graphene spin valve. This is like the graphene. There are some ferromagnetic detectors, and we place the bismuth tellurbromide crystal on top. Now, first, we wanted to characterize our graphene detector, and this is done by non-local spin valve measurements. I quickly guide through how this works. So, for example, here is a magnetic contact where the magnetization lies in the direction of the contact, engineered by shape anisotropy. Now, what you do is that you inject the current away from where you want to detect a spin current. This is where you detect the non-local voltage. So the charge current flows in this way, but there's also a spin current diffusing in this way, which you detect with a voltmeter, so which is another ferromagnetic contact. Now, the idea is that what you detect is really the non-equilibrium spin-dependent chemical potential here. So what you can do is that you can switch these ferromagnetic detectors with the By field, which is shown here. So a magnetic field in the direction of the contacts. And such measurement is shown, for example, here. Here is the non-local voltage or something proportional to it, the non-local resistance shown. What you see is that at large negative field, the two ferromagnetic contacts, the injector and the detector, are aligned. And at some point, the two detector, one of them, let's say the injector switches, you have a different voltage. And then when both are aligned again, you recover the same signal. So this shows that there's a spin current flowing in the channel, which you detect with another electrode. Now, what we can do in this setup, that we can compare the graphene, which is covered by the bismuth tellurbromide, with a segment which is let's call it a reference segment, just by measuring with different ferromagnetic contacts. To be a bit more quantitative, what we have done is a Hanle precession measurement. Here, the idea is that you apply an out-of-plane magnetic field. So if you inject spins from this contact, which are in plane, they start to precess along their travel. And depending on at which angle they arrive at your contact, they will have larger or smaller contribution. So in a really naive picture, in a 1D ballistic case, you would expect a cosine-like oscillation as a function of magnetic field. However, this is, first of all, not a ballistic system, but a diffusive. So different electrons travel different lengths, which will lead to dephasing. Moreover, there's also spin relaxation. But at the end, by a simple 1D block equation model, you can fit these curves and obtain the spin relaxation length. Sorry, spin relaxation time is shown here. So what you can see here, that there are two segments shown, one which is covered by bismuth tellurbromide, this is the green one, and the one which is not covered by the bismuth tellurbromide, this is the blue one. And both of them has quite short spin relaxation lengths, typical for graphene on silicon dioxide, but the difference between them is not so much. So this is like within the scattering between different segments. Also, something else which I would like to highlight is that this is some charge transport in the segment which is covered and which is uncovered by the bismuth tellurbromide. The charge transport also looks more or less the same. The Dirac point is at the same point. So it looks like the bismuth tellurbromide doesn't do much with the graphene. There's no spin absorption taking place. There's no induced spin orbit interaction. So these two more or less is in the same order of magnitude if you compare to 10 picoseconds or less found for tungsten selenide or something similar samples. And the reason for this is that there's a large interface resistance between the bismuth tellurbromide and graphene. With 3 terminal measurements, you see that there we have some contacts on the bismuth tellurbromide flake. You can verify this and that we have interface resistances in the 20-30 kilo ohm range. So now in this case, there's no induced spin orbit interaction. We have a large interface resistance, which we have found in more or less all of the samples which we have made. This is not something we designed. This is there by itself, but this is quite reliably there for all our samples. So now let's see how to generate the spin current. So what you do is that you inject the current from the bismuth tellurbromide flake. Here you have a contact on it to one of the cobalt electrodes, and you detect the non-local voltage on the opposite direction. So here is the measurement shown. And what you have to see is that when you sweep the in-plane magnetic field, that you see a single switch. And this switch corresponds to the field when this detector switches. So this measurement shows that there's a spin current flowing in graphene coming from this, in principle, non-magnetic material. And we attribute this to the Rausch-Edelstein effect, where there's an electric field generated by the current and the finite resistance of the signal. The electric field is in this direction, which generates a perpendicular polarization, which you detect with the cobalt. Now, to try to prove this, we have rotated our geometry. Now the current flows in the opposite direction, hence the electric field changes. What one expects that the spin current should also switch. And this is what we see. If we detect the voltage now on the other signal, we see again a single switch corresponding to an opposite spin current. So now we can also test, there's a gate electrode below our system. We can test how it reacts to the gate electrode. To be honest, there's not much happening. If you look at these curves, they are quite noisy, but altogether, if you look, this is the size of the extracted spin signal. It doesn't change much as a function of the gate voltage. And I think we understand this. This comes from the fact that the crystal, the bismuth tellurbromide, is a rather metallic crystal. So gating of such thick and metallic crystals is quite impossible. Also, the interface resistance is dominating in the resistance system here. So we don't expect much of change of the non-local signal determined in graphene. Why we are also happy of this, because if you see that if you go from negative to positive gate voltages, you change the carrier density, the carrier type in graphene, whereas the non-local signal doesn't change type. So we can say that probably this disqualifies all kind of spurious Hall effect and so on from this. So one other thing we can do is that we can try to make a Hanle precession measurement. So now, again, we pass the current from, let's say, from this flake in this direction, and we apply an out-of-plane magnetic field and record the voltage here. And what you see here is that there's a voltage shown here, where there's I think a Hanle-like looking curve seen which changes sign when you change the sign of the detector electrode. Sorry, I put this away because interfere. So what we have noticed that there's a slight offset of this Hanle curves on zero magnetic field, which we didn't notice in previous measurements, so it was not related to our setup. And one thing which could explain this is shown here in the bottom panel. So here, if you have what is shown here is Hanle curves. So for example, the blue curves corresponds to a situation when the detector and the injector are parallel. In this case, when the magnetic field is zero, all the spins are parallelly transported from the injector to the detector, and you expect a maximal signal. Here is now the opposite case when the injector and the detector has a 90 degrees rotation with respect to each other. So in order to have a large spin signal, you have to rotate the spins from the injector to the detector. You have to apply a finite magnetic field. So you expect the maximum of the curve to be at finite magnetic field. And this corresponds to this green asymmetric curve. Now you can imagine that by using the Hanle theory, you can generate curves, different curves with arbitrary angle in between them. So here what you see is that this is like the curve which we have used for fitting, which contains the angle between them, polarizations, current resistance of the graphene, and this is like the precession term. And from this we obtained a 7-degree rotation, and this we were not surprised because the electric field determines in principle the direction of the spin polarization, and we know that our contacts are somewhere like this, and I can go back to show this. The contacts are placed a bit further away, so you don't expect that the electric field directly points in this direction. This is what we wanted also to show with this arrow a bit. So now, how reliable is this 7 degrees? This I doubt, but what you have to take into account that you average over different trajectories which produce different spin polarizations. We did some COMSOL simulations which are more or less agreement with what we show. What I would note that we also presented in our paper another device where we have seen everything which I have shown before similarly. And here the detector was even more out. So what you would expect that the electric field is even less perpendicular to the contacts. So you expect a larger field from the Hanle fitting. And this is in principle what we have seen. The Hanle curve is quite asymmetric, and you obtain a large angle. So as an outlook, what we are working on now is to try to take this under control, to average, to have different directions where you can inject the current and look at this angle dependence a bit better. So how big is this effect? Just to finish up, the effect is like quite small in this case. We were at the 0.1% polarization. We have some tunneling model simulations which are shown in the paper, which I will not have time to show now, but it's agreement with what we have shown. Now to boost the signal, either you have to apply larger electric fields, the resistance of this material is quite small, or you would have to decrease the density. That would be even nicer. So now, as I said, there's some challenge in gating these samples because these are thick ones. So either you try to exfoliate thin ones. This is like really challenging. I think we never went below 20 nanometers. But for bismuth telluriodide, there we had some study where we have shown that in principle, with a bit different method, you can achieve single layer. So it's not even impossible for bismuth tellurbromide. Here, the fabrication is a bit more involved. Or the other idea is to use ionic liquid gating. In one of the recent studies which we have put on arXiv, you can see that we also managed to use liquid gating to tune the density in bismuth tellurbromide. Here, the caveat is that the density will be probably not homogeneous in the flake. I will show one last slide and finish up. This is like what I want to show you is let's say, to look for collaboration. So this is our new endeavor. What we are starting now is to try to use a pressure cell to change the interlayer distance in van der Waals heterostructures. So here is our system where you can put a chip on a bonding pad and then put this to a pressure cell and put it into a hydrostatic pressure of 2-3 gigapascal. And here the idea, for example, in the study what we have started is to put a graphene on a tungsten selenide and apply hydrostatic pressure. And what we hope to believe that this curve shown, for example, is that the conductance as a function of magnetic field is that at small pressure you only have a small anti-localization. At large pressure, when the layers are closer to other, maybe the spin-orbit interaction is enhanced. So if someone is interested, we would be happy to collaborate with other people on structures where the interlayer distance might matter. So with this, I would like to finish up. So this is the team working on this project. So this is the Budapest team. Zoltán was the main contributor to this work. This work was done in close collaboration. In principle, the measurements were indeed done in Chalmers, so in the group of Saros Des. So we really acknowledge the fruitful work collaboration with them. And some works in the motivation which I showed was done in the group of Christian Schönenberger. With this, I thank you for your attention.
Thank you for the nice talk. So we are running a bit out of time, but we have a couple of minutes for questions. So we have 2 questions regarding the quality of the interface. So why is so from where is the oxidation coming from? So if you have the high resistance because of oxidation at the interface, and also if that is related to the proximity effect, the lack of proximity effect, or a huge Rajba-Edelstein effect of the interface.
So yes, to be honest, in the beginning of our studies, we also were hoping to have some proximity effect. We even done some low temperature magnetotransport measurements where we never saw any anti-localization signal. And more careful analysis showed that these interface resistances are always high. We never have done any control stacking in a I would say control stacking in a glove box where both flakes are exfoliated. If it's oxidation or not, I mean it's hard to answer for me. This crystal is polar, so I think anything from the air likes to stick to it. So it's in this sense it's not the best materials to stack because you really need, I think, an inert atmosphere to keep it clean. It's not obvious that it's oxidation what happens. It may be just things getting stick in between the graphene and the material.
I mean, in these materials, just export to air and will damage the surface, and then it will be critical for the device performance.
Yeah. Yeah. So I mean, to go on with such devices, I would say that one would need a better controlled interface. Like, for example, you could use a boron nitride. I would say that at this point, the main aim of us was to show that you can generate a spin current or a spin population in the bismuth tellur bromide, for which the graphene spintronics was really useful because this is now at control at hand. Now, how to put these systems together? As I say, probably there you need better control. Here, really, the graphene was a detector for us.
Okay, and did you try to anneal the system, like putting some current, so do some current annealing to improve the interface quality?
Yes. So okay. So like if you anneal in a chamber, these crystals are degrading. So that's at least it's at a certain temperature. If you do current annealing, so you pass a current from the flake to the graphene, sometimes we have seen that the interface resistance lowers, and maybe I would even say, but this was only one sample, that we have seen that the spin signal in graphene disappeared, which I would say is a sign of spin absorption. But this we have to analyze a bit more or do more measurements. This is, I mean, it's a bit uncontrolled, so not all the samples survive such processes.
Okay, thank you. So I'm afraid we should move to the next speaker. So thank you for the presentation. And the last talk of the day would be from Franz Herrling from Felix Casanova Group. So he will talk about the gate tunability of high efficient spin to charge conversion by spin Hall effect in graphene proximized by tungsten diselenide.
Yeah, thank you for the introduction. I hope you can hear me and you can see the screen. I want to thank for the opportunity for our group to present the results on spin-to-charge conversion in 2D materials. And while I'm on the title slide, I also want to thank all the people in the Nano Devices group at Nanogune that contributed to this work. And I want to thank the European Union for the funding of my PhD through the Questec Innovative Training Network. Yeah, thanks to the 2 talks we already heard before, I don't have to give too much introduction to 2D materials or spintronics, and I rather want to explain why our group is interested in combining 2D materials for spintronic applications. And the most well-known material is probably graphene, that already has been topic of this session, where we find a long spin diffusion length of tens of micrometers up to room temperature due to the weak spin-orbit coupling in graphene. And so graphene is a very good material for spin transport in future spintronic devices. And another part of the 2D material family are transition metal digicogonaids, TMDs, and that have strong spin-orbit coupling, and recently also have been shown to show spin-to-charge conversion in the material. So they are a good material for injection and detection of spin currents. And both of these material groups can be exfoliated down to the monolayer. So so it's very interesting to combine them in van der Waals heterostructures. And we expect them to show proximity effects when we combine those 2 materials. And these proximity effects could be exploited to add functionality for spintronic devices. And one of these added functionality could be, for example, spin-to-charge conversion in graphene, where our group last year published the first experimental observation in a MOS2 graphene heterostructure, where we could show directly spin-to-charge conversion in graphene due to the induced spin-orbit coupling by the TMD on top. And this has been done in this Hall bar design of graphene with the TMD on top. And of course, the first question that arises from that is it possible to also use other TMDs? Can this be a platform, this design, to study spin transport in general in graphene and the effect of the interface and the proximity on the spin transport in graphene? The second thing we found in this paper is that the size of the output signal is not only related to the spin Hall angle, but rather to the product of the spin Hall angle and the spin diffusion length. And this has already been topic in the talks of this session as well, that this figure of merit and how to determine which material is better than another is quite a complex discussion. And of course, here the question is, can we increase this output signal? Can we increase this figure of merit of this theta times lambda product? And the last question that arose from our findings last year was that there is theoretical predictions of electrical control of this spin-to-charge conversion. There has been a theory paper where they study the spin Hall conductivity in this case, plotted versus the Fermi energy of the material for different TMDs. And we can see for some of them that changing the Fermi energy is actually changing the size and also sometimes the sign of the spin Hall conductivity. So it should be possible via a backgate to tune this energy, and via this also tune the spin Hall effect. So this has been our outlook, what we wanted to do. And the experimental platform for this is, like I mentioned, this double Hall bar design of graphene with a TMD on top. And is you can see an image on the right side. And the way we fabricate is that we exfoliate the graphene flake on silicon oxide. And then we try transfer the TMD on top of the graphene and anneal the whole structure. And in the next step, via e-beam lithography and reactive iron etching, structure the graphene into this double cross shape. And then via thermal deposition, contact it electrically and add cobalt titanium oxide electrodes for injecting spin currents into the graphene. And this platform gives us the chance to study the transport in the graphene via this lateral spin valve that we already seen as a reference graphene. And we have the lateral spin valve with the TMD on top to study the proximity effects. And lastly, we also have this Horber cross shape to measure the spin to charge conversion directly. And I want to start with the lateral spin valve and the Hanle precession that we have already seen. So here you can non-locally inject a current, a spin current that travels through diffusive through the graphene and is detected with a second pair of electrodes. And we have already seen that with a magnetic field in Y, you are able to control the states of this lateral spin valve. And in our case, with a magnetic field in X, not in Z, you are able to process the spin during the transport through the graphene, and you will be able to measure a non-local resistance versus this magnetic field in X. And what you see is this very standard symmetric Hanle curve, where you can see that the signal you measure is symmetric in X, and also for the two states for parallel and anti-parallel. And you see that the spin precesses into the out-of-plane configuration, and then for higher fields above 0.3 Tesla, the magnetization of the electrodes is actually pulled into the hard axis along X, and therefore also the spin is injected along X, and you detect the saturation for high fields for both states and both field directions. And what you can actually do now is that you take the difference between those two curves and you remove the background, as you can see, and this can be fitted to the one-dimensional diffusion equation. And the fit parameter that you get is the polarization of the injector and the detector. And for the spin transport, you get the spin diffusion time and the spin diffusion constant, which essentially gives you the spin diffusion length, as we've seen in the talks before. And this is an alternative to changing the length of the lateral spin valves, as we've seen in the theoretical talk, but that you can measure the those parameters in one lateral spin valve through the applied magnetic field. And if we compare these results to the results from the lateral spin valve, where we have the tungsten deselenide in the middle, we see that the Hanle curves are still symmetric, but the shape changes quite drastically. We have these enhanced shoulders for the midfield range. And the reason for those is that due to the anisotropy that is induced in the graphene, the spin lifetime for out-of-plane and in-plane spins is different. And this anisotropy is a clear sign that via proximity effect, the TMD enhances the spin-orbit coupling in the graphene. And this is actually what we expected. And this has been known. And if we have this increased spin-orbit coupling in the graphene, we also expect spin-to-charge conversion. And that's the main experiment I want to present, where we have in our structure, where we now replace one of the ferromagnet electrodes with this proximatized region in the graphene. As you can see here, we now measure the voltage across the graphene cross and still process the spin with a field along X. And what will happen is that due to the introduced spin-orbit coupling in the graphene, there is a sizable spin Hall effect. And due to the symmetries of the spin Hall effect, only spins that are pointing out of plane will be converted into charge. And that we then can measure across this graphene cross as a voltage. So if we now look at the resistance that we measure versus the field, we will see that this curve looks different. The signal will be 0 for low field. And then while we increase the field, the signal will increase because more and more spins are processing into out of plane until they reach the proximatized region. And then if you keep on increasing the field, the spins will keep on processing again into the plane. So the signal will decrease and you will have the same saturation as before, that for high fields, you will only inject spins along X and you will have no signal again. And this signal is antisymmetric in field because if you apply a field along X, the spins will process along Z. And if you apply at -X, the spins will process into -Z. So you will get a different sign in the resistance that you're measuring. And for the two states of the injection electrode, this signal is also antisymmetric. So you get this clear antisymmetric Harnley shape that is very different to the one that we measure in our reference lateral spin valve. And this is a clear experimental sign of the spin Hall effect inside of graphene due to the proximity-induced spin-orbit coupling by the tungsten deselenide. So again, we can now subtract the parallel and antiparallel state, or rather the two states of the injector electrode. And we can see that the output signal that we define here as the change in resistance as delta R SCC is quite large with 55 milliohms at 100K. If we compare this to our previous results in the graphene MOS2 samples where we had 12 milliohms, we see that we are like 4 times larger. And if we fit this data that we have to the 1D diffusion equation, we can get now the spin to charge conversion parameters, and we can actually look at this data more quantitatively and not just qualitatively. And the parameters that we extract are in this case actually not the polarization of the detector electrode, but the spin Hall angle, as we replace the detector electrode with this proximatized region. And we see we have a 2% spin Hall angle, which is rather small compared to the large output signal. But as I said, the interesting thing is that in graphene, the spin diffusion length is quite long. So if we now look at the spin diffusion length of our proximatized graphene, we see that this is rather large with 380 nanometers. And if we now take the product of theta times lambda, we see that we reach 7.6 nanometers. So this is the reason we can measure such large output signals in this TMD graphene heterostructure. For example, if we compare this to values we have seen in this session already in metallic system, for example, platinum is always a good benchmark, where this length is actually 0.2 nanometers. And with that, I come to the third part that I wanted to show in our experiments, and this is the gate tunability. So what we did, we measured the signal at 0 volts. You can see the antisymmetric Harnley curve. And if we apply to the sample via a backgate 5 volts, where we reach the charge neutrality point of the graphene, you can see that we essentially can turn off the signal inside of the noise level of our measurement. If we go away from the charge neutrality point by applying a negative gate voltage, the signal increases by up to 400%. And if we can amplify the signal, and if we show the trend between -5 and 5 volt, we can see that we can clearly control our spin to charge conversion signal with the gate voltage. What we couldn't do, but there has been a recent publication from the group from Valenzuela, where they can also change the sign. By increasing the gate voltage, you can change the sign of the spin to charge conversion, and you can actually reproduce this theoretical prediction that I showed in the introduction of the talk. What we did in the next step is to measure the spin to charge conversion for different temperatures from 10 to 300K. And what you can clearly see is that the signal increases for low temperatures, but is stable up to room temperature. So we can still at room temperature measure a quite robust signal. And if you look a little bit more into the quantitative analysis, you can see that the reason for this large signal at low temperatures is that the spin Hall angle is that we get is larger at low temperatures, but still up to 1.7% at room temperature. And the good thing about the system is that the spin diffusion length is still quite large at room temperature as well, almost 300 nanometers. This is not the long micrometer spin diffusion length that we see in pristine graphene, but it's still a lot longer than in metallic system. And this is the reason that the theta times lambda product, which is the figure of merit in this system, is still almost 5 nanometers at room temperature. So this makes it actually possible to use those 2D material systems for real-world application in spintronic devices, which will probably operate at room temperature, and where the theta times lambda product is way larger than comparable metallic systems that are normally used for spintronics. And the second thing I want to point out is the reason that we can control and amplify the signal with the gate voltage is actually the control of the spin Hall angle with the gate voltage. So we can see that at -5 volt, it increases by 400% up to 8.4%. And with this large spin diffusion length, we get actually a theta times lambda product of up to 40 nanometers, which is now two orders of magnitude larger than, for example, in platinum systems or heavy metals, and even larger than in the topological insulators that have been shown in this session. And with that, I want to come to the summary of the talk. I hope I could show that 2D materials, and especially Van der Waals heterostructures, are an interesting platform, not just to study fundamental physics, but also to, via the proximity effect, use added functionality in spintronic devices. And one of the functionalities I showed has been the spin-to-charge conversion by spin-Hall effect directly in graphene, where I showed that this effect is highly efficient, and we can control it electrically via a backgate voltage, and we can tune this theta times lambda product, the spin-Hall angle times the spin diffusion length, that is responsible for large output signals in real-world devices from 0 up to 40 nanometers. Also, this is robust up to room temperature, so it's possible to maybe one day do spintronic devices out of 2D materials. And this has been the results that we published recently in APL Materials. I put the reference at the bottom, and with that, I thank you for your attention and are ready for questions and comments. Thank you.
Thank you, Franz, for the very interesting talk on spin-to-charge conversion in proximized graphene. So we have the first question from Jose. Is asking, do the spin-Hall thing, so the spin-Hall angle send sign when you change from electron to Hall graphene? So
yeah, actually, this is the part that unfortunately we not been able to show here. So I don't know if you see my pointer. I will try to put it on now. Maybe it's okay like this, that you can see here in the top left in the inset on the left side that we were not able to go from Hall to electron regime in the graphene due to gate leakage. So we were not able to apply higher gate voltages. But what has been seen in this paper here that I put the reference up is that actually you are able at low temperatures to change the sign of the spin-Hall effect. I think at 100K, and it didn't change sign at room temperature when controlling the backgate and going from Halls to electron regime.
Okay, thank you. So the second question is if you have measured the spin lifetime anisotropy in graphene.
Yeah, so this is the other thing I kind of skipped. Some people may have noticed that when I compared the two data between the reference spin-Hall, reference lateral spin valve, and the proximatized one here in this case, that we were not able, we were able to measure the anisotropic harness shape, but we were not able to quantitatively fit it. The reason for this is that in the diffusion equation, the overlap between the parallel and anti-parallel curve actually gives you the anisotropy. So it's always expected that those two curves overlap. And as you see in the inset on the left side, in our case, they didn't overlap. So we were not able to extract the out of plane and in plane lifetime. So the kind of the anisotropy ratio for the graphene, and due to those two curves not overlapping. And we wrote in the paper a whole page in the supplementary information why this could be, things we came up with about the alignment of the sample with the magnetic field. But at the end, the conclusion was that we don't know why this is happening. And this is something that was unexpected. And this kind of prevents us to qualitatively study the anisotropy that is introduced, but which has been done in other experimental studies of graphene and TMDs to look at the ratio of in plane and out of plane lifetime, and even controlling it with a gate voltage.
Okay, thank you. We have another question from Lauren Villa. So it says that you presented the figure of merit in terms of the product of the lambda, so the lambda with the spin-Hall angle, but the output voltage you will need to you will need a very large spin diffusion length contacts. So the voltage should be divided by the lambda as well.
Now, in this case, if we look at the design, then what is interesting is the spin current that reaches the proximatized region. So of course, in some sense, the spin diffusion length of this graphene or whatever spin transport channel you're using, copper, for example, is interesting because it determines how much spin current is actually reaching your spin to charge conversion region. But then if you look at how much of this spin or how efficiently the spin current is converted into charge, then the two main parameters are the spin Hall angle and the spin diffusion length of this region. So essentially that most of the conversion is taking place in a length scale of the spin diffusion length of the proximatized region, or if you have a Rashba system, essentially of the Rashba parameter. And then when it's converted into charge, now, of course, the charge properties of your channel. So in this case, the resistance of this graphene cross where you pick up the voltage determine, of course, what kind like the value that you're picking up from this from spin converted into charge. So then here, I don't see how the diffusion, spin diffusion length is playing a role.
Yeah, I guess the question is related to the fact that you would need to have also very long electrodes to actually be able to convert and
yeah. So what you will see is that this region has to be around the length of your spin to charge conversion. Yeah.
It also makes me to wonder how can you distinguish in your device that you are having the spin to charge conversion in the graphene, not in the tungsten telluride. So can you distinguish?
Yeah, you can distinguish. So there's essentially three cases that can happen to the spin to charge conversion. It's the spin Hall effect directly in the graphene, and there is the spin Hall effect in the TMD. And the third one is, of course, Rashba-Edelstein effect at the interface. And the last two have a different symmetry in the spin to charge conversion than the spin Hall effect in graphene. So what you can easily always think of is that the spin Hall effect has this right-hand rule of spin current, magnetic field, and resulting like spin current direction, spin polarization, and resulting charge signal, and that this will be different in the graphene than if it's absorbed into the TMD. Then of course the direction of the spin current changes, and then this right-hand rule changes. So what you essentially see is that in the data you would see I'm going to just go forward to this slide. Now we see this antisymmetric precession, and for spin Hall effect in the TMD and for Rashba-Edelstein effect, the resulting signal would be a step in the big background signal, essentially when the signal for in plane along X is switching from minus to plus. So you can easily distinguish between spin Hall effect in graphene and the other two effects. What you cannot do in this measurement configuration is distinguish between spin Hall effect in the TMD and Rashba-Edelstein effect at the interface, because those two have the same symmetry. What other groups did is control this via the gate, that you control the conductivity of the TMD, the electrical conductivity, and that you then assume that if you tune the TMD to be not electrically conducting, that it will also not absorb spin, and then there will be no spin Hall effect in the TMD. So everything that you see besides the spin Hall effect in graphene will be Rashba-Edelstein effect. So that's kind of how you can separate those three spin to charge conversion mechanisms.
Okay, thank you very much. I think we have another question, but I think we can do this informally out of the formal part of the session. So with this, I would like to thank all the speakers for the very nice talks that you gave today, and also would like to remind that we have in this afternoon, we will have a pre-recorded talk session, and tomorrow also at 9:30 we will have a live stream conference session. And with this, I will also allow you to switch on the cameras if you would like, and also have an informal interaction. So thank you very much for your contribution today in the session. We have a question from Amilcar to Franz. So yeah.
Actually, now that I stopped sharing the screen, I can see the chat, which is quite helpful to actually read the question myself. And it's an interesting question, but I don't really know the answer to it.
So I think everybody can switch on the microphone if you would like.
Okay. So maybe I can elaborate directly what I mean.
Yes.
So, yeah, usually in this part, when you have the proximitized graphene, you will usually have this spin to charge conversion, but you will have also, you have spins that flow through the graphene. You will have a region, in this region, you will have also the conversion, and you will have already converted charges that flow across the T junction. So I'm just wondering if, because in the model, you assume that everything happened at once and then you do it. So my question was if you have some statistics of how this effect will happen if you have long flakes or just round flakes or something like this. How if you can, find some clue, because I think it's a difficult question.
Yeah. I think one part is connecting to the question that has been asked before you about the length, the spin diffusion length also playing a role in the contact length. So essentially, most of our studies, the proximitized region is longer than the spin diffusion length. So you can kind of assume that almost all of the spin is converted to charge inside of this region. And of course, then there is like still a region inside of this lambda length scale where spin to charge conversion happening, spin diffusion and charge diffusion. But that would be interesting to also think about from like a theoretical standpoint, what can actually happen in this region then, and what happens now that you have this long spin diffusion length in the graphene, that you could probably make the region smaller than this spin diffusion length, where not all of the spin has been converted, and what happens then if you're going like below this lambda for the width of the proximitized region. But actually, I'm not sure what could happen.
Okay, thanks.
Can we ask questions to the other speakers?
Yeah, if there is any question to any of the other speakers, if they are available, and so yeah, you could. Also.
I had a question for Laurent, but I missed. I didn't have time to write it before you switch. Laurent, are you here?
Yeah, of course.
Okay, so I wanted to ask you a general question about bringing some of your results to room temperature. Which are the perspective? Because these at least the best results with DEX are best at low temperatures, right?
Yes. So maybe to just follow up on my question, the output voltage will be basically the R squares times lambda. So this was my question. If you need very wide width, then the number of R square in the contact diminish, so the output voltage does not rise. In the case of STO, LAO, or all those systems, we indeed have much lowering of the lambda when we go up in temperature. We lose also the gate tunability because the dielectric constant is not large enough to allow